Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the cold reaches beyond Neptune, where a visitor from another star system glides silently through our corner of the galaxy. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. The comet arrives without fanfare, without sound, without the slightest acknowledgement of boundaries or borders between stellar neighborhoods. It has been falling toward the sun for longer than human civilization has existed, pulled by gravity's patient insistence across distances that dwarf the span between Earth and its star. This object, catalogued as 3I/Atlas, the third confirmed interstellar visitor to our solar system, carries with it dust and ice from a place no human eye will ever see. From a molecular cloud that collapsed into stars and planets in a region of the galaxy our sun has never visited and never will. The comet does not know it is being watched. It does not register the telescopes on distant Earth that track its motion against the background stars, measuring its velocity, calculating its trajectory, confirming what the numbers already whisper. This is no native wanderer. Its orbit is hyperbolic, unbound, a one-way passage through the solar system's outer precincts. It came from somewhere else. It will return to somewhere else. The in-between is brief, a cosmic eye blink, a window measured in months during which human instruments can gather light and attempt to decode what this traveler has brought from the dark. Only took 4.5 billion years for us to notice visitors like this. In the blackness beyond the Kuiper Belt, where sunlight weakens to a pale suggestion and the solar wind begins to lose its authority. The comet moves through space that is not quite empty. Hydrogen atoms drift in the interstellar medium, 1 or 2 per cubic centimeter, a density so rarefied it would be considered a perfect vacuum in any terrestrial laboratory. Cosmic rays, protons and heavier nuclei accelerated to near light speeds by supernovae and pulsars, sleeting through the galaxy. Strike the comet's surface, breaking chemical bonds, darkening ices, creating new molecules in the frozen crust. For millions of years, perhaps tens of millions, this object has bathed in radiation from distant stars, accumulating damage and alteration in silence. The comet's nucleus, the solid heart beneath the temporary veil of gas and dust it will soon wear, measures perhaps a kilometer across, perhaps less. The uncertainty lingers because direct imaging at such distances reveals only a point of light, a pixel, a smudge that refuses to resolve into detail. What can be measured is brightness, color, the rate at which that brightness changes as the comet tumbles through space. These measurements suggest a surface dark as charcoal, covered in organic residues and refractory grains, material that absorbs sunlight rather than reflecting it. Most comets are dark. This one is darker still. The darkness is not metaphorical. The albedo, the fraction of sunlight reflected rather than absorbed, hovers near 3 or 4%. Fresh asphalt reflects more light. The comet's surface has been processed, cooked by cosmic rays and UV photons, transformed into complex carbon-rich compounds that drink light and give back almost nothing. This is what happens to ice and organics when they spend geological ages in interstellar space. They age, they darken, they forget the brightness of the stellar nursery where they formed, somewhere in the constellation Ursa Major, in a direction the comet has traveled from. There exists, or once existed, a stellar system. Perhaps a young star still surrounded by its protoplanetary disk. Perhaps an older star whose planets have long since settled into stable orbits. Perhaps a binary system. Two stars locked in gravitational embrace, their combined mass sculpting the disk of gas and dust that birthed this wanderer. The details are lost to distance and time. What remains is the comet itself, an archive written in ice and stone, a message in a bottle thrown across parsecs. It drifts inward. The sun's gravity, weak at such distances, but inexorable, bends the comet's path, curves it gently toward the inner solar system. The object does not resist. It cannot. It obeys the mathematics of motion, the differential equations that govern every falling thing. Its velocity increases. Space around it begins to change character as the solar wind strengthens, as the density of solar photons rises, as the temperature, still bitterly cold by human standards, begins its slow climb from 3 Kelvin towards something slightly less absolute. And then, at a distance still beyond the orbit of Jupiter, something happens. The comet begins to wake. Ice buried beneath the surface, shielded from direct sunlight by layers of dark crust, begins to warm. Water ice remains frozen. The comet is still too far, too cold, but other ices, more volatile, less stable, begin to sublimate. Carbon monoxide, carbon dioxide, methane. These molecules, locked in solid form for millions of years, transition directly from ice to gas, bypassing the liquid phase entirely. The gas finds pathways through the porous crust, seeps upward, escapes into space. As it rises, it carries with it tiny particles of dust, grains smaller than the width of a human hair, fragments of the primordial material from which the comet was assembled in that distant, unknown system. The coma forms, a cloud of gas and dust, tenuous but vast, surrounds the dark nucleus. Sunlight strikes this cloud and scatters. Some photons bounce off dust grains and continue outward into space. Some are absorbed. Some, a particular subset, emerge with their electric fields aligned, polarized, carrying information about the size and shape and composition of the particles that redirected them. This is where the mystery lives. This is where the data becomes strange. Astronomers on Earth, operating polarimeters attached to telescopes in Chile and Hawaii and the Canary Islands, begin to collect light from the comet. They measure not just brightness, but polarization, the degree to which scattered light vibrates in a preferred direction. For most comets, the polarization signature follows predictable patterns. Small dust grains, irregularly shaped, scatter light in ways that depend on the angle between the sun, the comet, and the observer. Theory predicts, observations confirm. The universe, in this small corner of astrophysics, behaves as expected. 3I/Atlas does not behave as expected. The polarization curve, plotted as a function of phase angle, the Sun-Comet-Earth angle, shows features that do not match the standard models. At certain angles, the degree of polarization is too high. At others, it dips into negative values, a regime where light polarized perpendicular to the scattering plane dominates. The inversion angle, the phase angle where polarization crosses from negative to positive, occurs at an unexpected location. The slope of the curve in the positive branch is steeper than models predict for typical cometary dust. Something about the dust in this comet's coma is different. Something about the grains, their size distribution, their composition, their structure, their porosity, deviates from the population of particles found in solar system comets. The difference is not dramatic. It is not a contradiction of physics. It is a whisper, a subtle signature, a hint that the place where this comet formed operated under slightly different rules, or assembled materials in slightly different proportions, or processed dust through mechanisms that left their mark in ways that persist across interstellar distances and millions of years. The scientists write papers. They construct models. They debate whether the anomaly reflects truly alien dust or whether solar system comets, if observed with sufficient precision, might show similar diversity. The mystery does not resolve. It deepens, quietly, in the spaces between certainty and speculation. The comet continues inward, indifferent to the attention, indifferent to the questions it raises. It has been traveling for so long that a few months near a stranger's star hardly register as significant. It will leave. It will return to the dark. The polarization signature, unexpected and unexplained, will fade from telescopes and persist only in data archives, in tables of numbers, in figures published in journals that will themselves one day be forgotten. But for now, in this moment, the light scattered from ancient dust carries information across the void. Photons that left the sun 8 minutes ago, that bounced off grains formed in another stellar system, arrive at detectors cooled to eliminate noise, and the pattern of their polarization tells a story no one can fully read. Only took us a few thousand years of astronomy to build instruments sensitive enough to notice. The universe is patient. The comet does not hurry. The data accumulates, one photon at a time. Light does not travel in straight lines through empty space. This much has been known since Einstein. But for photons crossing the relatively flat space-time between a comet and a telescope, the deviation is negligible. What matters more, what shapes the character of the light that reaches Earth, is the series of interactions those photons undergo with matter. A photon leaves the sun's surface, unpolarized, its electric field vibrating in all directions perpendicular to its path. It crosses the inner solar system in 8 minutes, passes Earth's orbit, continues outward for hours until it strikes a dust grain in the coma of 3 Atlas. The grain is small, perhaps 1/10 of a micron across, perhaps a full micron, perhaps 10. The size distribution is not uniform, and this fact alone carries information. In the molecular cloud where the comet formed, dust grains grew through accretion, through sticking collisions, through the gradual accumulation of ice mantles on refractory cores. Some grains remained small, their growth arrested by turbulence or radiation pressure or simple statistical chance. Others grew larger, aggregating into fluffy structures with densities lower than water, porous assemblies of smaller particles held together by van der Waals forces and frozen volatiles. When the photon strikes such a grain, the encounter lasts only an instant, but the outcome depends on the grain's properties. If the grain is much smaller than the photon's wavelength, Rayleigh scattering dominates. The photon bounces preferentially at right angles, and the scattered light emerges polarized. If the grain is comparable to or larger than the wavelength, Mie scattering takes over, and the polarization pattern becomes more complex, exhibiting interference effects and forward scattering lobes. If the grain is irregular, fractal, porous, the interaction becomes nearly impossible to model analytically, and scientists resort to numerical simulations, approximations, educated guesses. The photon that scattered from the grain in 3 Atlas's coma now travels toward Earth. Its electric field oscillating preferentially in one direction, it is now polarized. Millions of such photons, scattered from millions of grains, arrive at a telescope on Mauna Kea or Cerro Paranal or La Palma. A polarimeter, a device incorporating waveplates and polarizing filters, measures the orientation and degree of this polarization. The data, reduced and calibrated, becomes a point on a graph. Many nights of observation produce many points. A curve emerges. The curve does not look like the curves from other comets. This is the quiet anomaly. This is the signature that resists easy explanation. The polarization of sunlight scattered by cometary dust typically follows an empirical relationship discovered decades ago, refined through observations of hundreds of comets. At small phase angles, when the Sun comet and Earth are nearly aligned, polarization is negative, meaning light polarized perpendicular to the scattering plane dominates. As the phase angle increases, polarization crosses through zero at the inversion angle, then rises into positive values, reaching a maximum around phase angles of 90 degrees before declining again at larger angles. For solar system comets, the inversion angle clusters around 20 degrees. The maximum polarization, expressed as a percentage, rarely exceeds 30%. The slope of the polarization curve in the positive branch correlates with other properties. Comets with steeper slopes tend to have larger, fluffier dust grains. These relationships, while empirical rather than derived from first principles, hold across a wide range of cometary types. They are robust, they are predictable. 3I/Atlas shows an inversion angle closer to 25 degrees. The maximum polarization exceeds what models predict for the observed brightness and color. The slope is steeper, suggesting either larger grains or a different refractive index or a porosity structure not commonly found in solar system comets. The negative branch, measured at small phase angles, is deeper than expected. Perhaps the dust formed around a star with a different metallicity, a different ratio of carbon to oxygen, a different inventory of available elements. Perhaps the comet's birth cloud was colder, allowing more volatile ices to condense and coat the grains, changing their optical properties. Perhaps the millions of years spent in interstellar space altered the grain surfaces in ways that solar system comets, nestled always within the Sun's protective heliosphere, never experience. Or perhaps solar system comets show similar diversity, and 3I/Atlas simply falls at one end of a distribution that has not yet been fully sampled. Only a few thousand comets have been observed well enough for polarimetry. Only a tiny fraction of those have been studied across a wide range of phase angles. The data set, for all its richness, remains incomplete. The uncertainty does not frustrate the scientists, it invigorates them. Every anomaly is an invitation. Every deviation from prediction is a doorway to deeper understanding. They write proposals for more telescope time. They refine their models, adding parameters for grain porosity, for ice-to-dust ratios, for size distributions that differ from the standard power law. They compare 3I/Atlas with 2I/Borisov, the previous interstellar comet, and with 1I/Oumuamua, the first detected interstellar object, which showed no cometary activity and remains enigmatic. Only took us until 2017 to confirm the first interstellar visitor. Only took a few more years to find the next ones. Only a matter of time before the catalog grows long enough to reveal patterns, families, categories of objects that share common origins or evolutionary paths. The comet moves through space at 17 kilometers per second relative to the Sun. This velocity is unremarkable for an interstellar object, the local standard of rest. The average motion of stars in the solar neighborhood implies typical velocities of a few tens of kilometers per second. What makes the trajectory notable is its geometry. The orbit is tilted steeply to the ecliptic, the plane where planets orbit. The comet approaches from above, dives through the inner solar system at an angle, and departs below, never coming particularly close to any major planet. Jupiter's gravity barely touches it. Saturn's influence is negligible. The Sun alone governs its path, bending the hyperbola just enough to send the comet back into the galaxy on a slightly different heading than it arrived. Where it goes next is unknown. Will it pass near another star in 10,000 years? 100,000? Will it drift through the interstellar medium for millions of years, accumulating more radiation damage, darkening further, until some future stellar encounter perturbs its orbit again? Will it fragment under the stress of thermal cycling, splitting into smaller pieces that disperse along slightly different trajectories? Or will it remain intact, a single frozen archive, carrying its cargo of pre-solar grains and interstellar organics through the Milky Way until the galaxy itself evolves beyond recognition? These questions have no answers. The comet will not report back. It will simply continue, governed by gravity and momentum and the slow decay of unstable isotopes in its interior. Back on Earth, the polarization data is published. The paper appears in a journal, is read by a few hundred specialists, is cited by a handful of subsequent studies. The unexpected signature is noted, hypotheses are proposed, follow-up observations are planned. Though the comet is already fading, its coma thinning as it moves away from the sun and volatile sublimation decreases. Within a year, it will be too faint for detailed study. Within 2 years, it will be undetectable except by the largest telescopes. Within a decade, it will be lost entirely. A receding point of light swallowed by distance and the brightness of background stars. But the light has already been captured. The photons, twisted by ancient dust, have been measured and recorded. The polarization signature, unexpected and unresolved, persists in digital files, in archived spectra, in tables of calibrated observations. The comet may vanish, but the data remains, waiting for future instruments, future models, future insights that might finally explain what made this visitor different. The grains themselves, the actual physical particles that scattered the light, continue their own journeys. Some fall back toward the nucleus, reabsorbed into the coma's gravity well. Others escape entirely, pushed outward by radiation pressure, forming the comet's tail. 2 tails, actually. One of ionized gas swept back by the solar wind. One of dust following a curved path determined by the balance between gravity and light. The dust tail spreads along the comet's orbit, a faint trail that will persist for years after the comet itself has departed, slowly dispersing as the particles drift apart under the influence of planetary perturbations and galactic tides. A few of those grains, perhaps, will be swept up by Earth's atmosphere in some future century, burning up as meteors, their atoms mingling with terrestrial air. A traveler from another star system, reduced to plasma in the upper atmosphere above some unsuspecting city or ocean, its origin forever unknown to the people who might glance up and see a brief streak of light and think nothing more of it. Only the universe keeps track of such trajectories. Only gravity and momentum remember where things came from and where they are going. The comet does not look back. The light continues to scatter. The polarization, unexpected, persists in the data, a whisper from another stellar nursery, a message delivered in the language of twisted photons and micron-sized grains. The ice that sublimates from 3 Ice/Atlas's nucleus is not water, not yet. Water ice, stable and abundant in comets throughout the solar system, requires warmer temperatures to transition from solid to gas at the pressures found in the near vacuum of space. At the comet's current distance, several astronomical units from the Sun, the surface temperature hovers around 150 Kelvin, cold enough to keep water locked in solid form, but warm enough to mobilize more volatile species. Carbon monoxide leads the exodus. This molecule, composed of 1 carbon atom bonded to 1 oxygen atom, freezes at temperatures below 68 Kelvin at the pressures of interstellar space. As the comet warms, CO ice buried beneath the surface begins to sublimate, the molecules vibrating free from their lattice positions and streaming upward through cracks and pores in the crust. Carbon dioxide follows, slightly less volatile but still eager to escape at temperatures above 100 Kelvin. These gases, invisible to human eyes, carry energy away from the nucleus, cooling the interior even as the surface warms. creating temperature gradients that stress the structure and may eventually lead to fracturing. The outgassing is not uniform. The nucleus rotates, tumbling through space with a period that observations suggest might be 8 or 9 hours, though the uncertainty remains significant. As different regions rotate into sunlight, local heating drives local sublimation, creating jets of gas and dust that spray into space from active areas while other regions remain dormant. This asymmetric outgassing exerts forces on the nucleus, tiny rocket-like pushes that alter the comet's trajectory in ways too small to measure directly, but large enough. Accumulated over months. To introduce errors into predictions of the orbit, only took a few centuries of celestial mechanics to realize comets don't follow perfect Keplerian orbits. The gas expands into the coma at speeds determined by temperature and molecular mass. Carbon monoxide, light and energetic, moves faster than carbon dioxide. Both move far faster than the dust grains they carry along, which are accelerated by collisions with gas molecules and by radiation pressure from sunlight. The coma grows, extending tens of thousands of kilometers from the nucleus, a vast but tenuous cloud where the density of molecules is still lower than the best vacuum achievable in terrestrial laboratories. Within this expanding cloud, chemistry happens. Sunlight, particularly ultraviolet photons energetic enough to break chemical bonds, strikes gas molecules and dissociates them. Carbon monoxide splits into carbon and oxygen atoms, water molecules. When they eventually join the outflow at smaller heliocentric distances, break into hydrogen and oxygen, into hydroxyl radicals, into a cascade of reactive species that recombine and react and create daughter molecules never present in the original ice. Some of these products are ionized by solar UV, stripped of electrons, becoming charged particles that interact with the solar wind's magnetic field, the solar wind itself. The stream of charged particles flowing outward from the sun's corona at hundreds of kilometers per second begins to interact with the comet's ionized coma. At large distances, this interaction is gentle, a gradual pressure that shapes the ion tail and drapes magnetic field lines around the coma like a wind flowing around an obstacle. Closer to the sun, the interaction becomes violent, forming bow shocks and magnetotail structures. But 3I/Atlas will never approach closely enough for such drama. Its perihelion, the closest point to the sun, lies beyond Earth's orbit, a relatively distant passage that limits the comet's activity and keeps its display subdued. This muted activity is both a limitation and a gift. A brighter, more active comet would be easier to observe, would produce more data, would scatter more light for polarimeters to analyze. But a brighter comet would also be more altered by solar heating, its surface processed and transformed by intense sublimation, its primordial characteristics obscured by the violence of close approach. 3I/Atlas, remaining distant, retains more of its original character. The dust that populates its coma has been less modified by thermal stress. The ice that sublimates carries a more faithful record of the volatile inventory from its birth cloud. Scientists use spectroscopy to inventory the molecules in the coma. Each species absorbs and emits light at characteristic wavelengths, creating a unique fingerprint in the comet's spectrum. Carbon monoxide shows strong emission lines in the ultraviolet and infrared. Cyanogen, a molecule composed of carbon and nitrogen, appears in visible wavelengths. Water, when it finally begins sublimating at smaller distances, dominates the spectrum with its many vibrational and rotational transitions. The relative abundances of these molecules tell a story about conditions in the comet's formation environment. The ratio of carbon monoxide to water, for instance, varies widely among solar system comets, depending on where in the protoplanetary disk they formed and how much heating they experienced before being scattered into distant orbits. Comets from the Oort cloud, The spherical shell of icy bodies surrounding the solar system at distances of tens of thousands of astronomical units tend to be co-rich, having formed in the coldest regions where carbon monoxide ice could condense. Kuiper belt objects, formed closer to the Sun in the realm beyond Neptune, show different compositions. 3 Ice/Atlas shows a Kyoto-water ratio that falls within the range observed for solar system comets, but toward the higher end, suggesting formation in a cold environment. Whether that environment was colder than the outer regions of our own protoplanetary disk, or simply similar, remains unclear. The data does not provide enough leverage to distinguish between these scenarios. The comet could be a twin of solar system objects, formed under nearly identical conditions in another stellar nursery, or it could be subtly different, a product of variations in disk temperature or composition or dynamics that leave only faint traces in the observables. The uncertainty is not a failure of the observations. It is a reflection of how much remains unknown about planet formation in general, about the diversity of protoplanetary disks across the galaxy, about how sensitive final compositions are to initial conditions and evolutionary paths. Thousands of exoplanets have been discovered orbiting other stars, but protoplanetary disks remain difficult to observe in detail, and the connection between disk properties and the comets that form within them remains largely theoretical. Only a few dozen protoplanetary disks have been imaged with sufficient resolution to see gaps and rings and spiral structures. Only a handful have been studied well enough to measure molecular abundances in the gas phase. The catalogue of what is possible, what is common, what is rare in disk chemistry and dynamics remains sparse. The organic molecules in the coma add another layer of complexity. Comets are known to carry complex carbon-based compounds, some as simple as methane and methanol, others as intricate as amino acids and polycyclic aromatic hydrocarbons. These organics, formed through a combination of gas phase chemistry in the stellar nursery and radiation-driven processing on grain surfaces, represent a chemical inventory that predates the formation of planets, that connects to the molecules found in dense molecular clouds throughout the galaxy. Spectroscopic surveys of 3 Ice/Atlas detect several organic species, though the list is incomplete and biased towards molecules with strong emission or absorption features. Hydrogen cyanide appears, as does formaldehyde. Methanol is suspected but not confirmed. The presence of these molecules is expected. Solar system comets show similar inventories, but the relative abundances. The ratios between species may encode information about the chemical pathways active in the comet's birth environment. Some organics are synthesized in the gas phase, through reactions between simple molecules in the warm, dense regions of collapsing clouds. Others form on the surfaces of dust grains, where hydrogen atoms stick and migrate and react with carbon monoxide or carbon dioxide to build more complex structures. Still others are created by UV photolysis and cosmic ray bombardment of ice mantles, processes that break bonds and create radicals that recombine into new configurations. Disentangling which pathways dominated in 3 Ice/Atlas's formation environment requires detailed modeling and comparison with laboratory experiments, work that is ongoing and incomplete. The comet continues inward, oblivious to the questions it raises, oblivious to the scientific effort devoted to understanding its composition and origin. It simply sublimates, releasing gas and dust according to the physics of heat transfer and vapor pressure, creating a coma that grows and brightens as solar flux increases. The polarization signature persists, encoded in the scattered light, waiting to be measured again as the phase angle changes. As the comet's position relative to Earth and Sun shifts along its trajectory, more observations are planned, more data will be collected. The archive will grow, the uncertainties will narrow, the models will be refined. But the essential mystery, what made this comet in this distant system? What processes governed its assembly? what history it carries in its ice and organics, will remain incompletely resolved. The comet will not confess its secrets easily. It will offer clues, hints, suggestions, and the scientists will assemble those fragments into hypotheses, into scenarios, into narratives that are always provisional, always subject to revision when new data arrives. Only the comet knows its own history, and the comet does not speak except through light and molecules and the subtle signatures of its dust. The journey from another star system is not a journey in any experiential sense. There is no landscape to traverse, no milestones to pass, no sense of progress or destination. There is only motion, relentless and unchanging, governed by the velocity the comet acquired during its ejection from its birth system and modified only slightly by the feeble gravitational tugs of stars it passes at vast distances. For millions of years, 3I/Atlas drifted through the galaxy, a speck of ice and rock moving through an ocean of near emptiness, encountering almost nothing, changing almost not at all. The interstellar medium is not truly empty. Hydrogen atoms, the most abundant element in the universe, drift in the space between stars at densities averaging about 1 atom per cubic centimeter in the galactic disk. In molecular clouds, where stars form, densities can reach hundreds or thousands of atoms per cubic centimeter. In the hot ionized gas between spiral arms, densities drop to 1 atom per 100 cubic centimeters or less. The comet, moving at roughly 20 kilometers per second relative to the local standard of rest, encounters these atoms as a gentle wind, an interstellar breeze that exerts no measurable force but delivers a steady rain of impacts on the nucleus surface. Each hydrogen atom that strikes the comet carries kinetic energy proportional to its velocity. At 20 kilometers per second, this energy is small, insufficient to vaporize ice or eject material, but not negligible. Over millions of years, the cumulative effect of countless atomic impacts contributes to surface erosion, to the gradual sputtering away of the outermost layers of the nucleus. This process is slow, removing perhaps a few centimeters of material over the entire interstellar journey, but it is real, and it preferentially removes lighter elements, leaving behind a surface enriched in heavier, more refractory components, cosmic rays. 2. Bombard the comet throughout its journey. These high-energy particles, mostly protons and helium nuclei accelerated to relativistic speeds by supernova shocks and other violent events, penetrate deep into the nucleus, far beyond the reach of surface sputtering. When a cosmic ray strikes an ice molecule, it deposits energy, breaking chemical bonds, creating free radicals, ionizing atoms. The products of these interactions recombine into new molecules, some of which are stable, others of which remain reactive and participate in further chemistry. Over geological timescales, cosmic ray processing alters the chemical composition of cometary ice. Simple molecules like water and carbon monoxide are partly converted into more complex species. Methane becomes ethane, then propane, then longer hydrocarbons. Ammonia reacts to form nitrogen-bearing organics. The ice darkens as carbon-rich residues accumulate, as the radiation-resistant components concentrate while volatile products slowly sublimate away even in the cold of interstellar space. Only took the solar system about 5 billion years to produce instruments capable of detecting cosmic ray damage in comets. Only took evolution a few billion years to produce organisms capable of understanding what cosmic rays are. The darkening is not uniform. Cosmic rays penetrate to depths of meters, but their flux and energy spectrum create a gradient. With the highest radiation dose in the outermost layers, deeper ice remains more pristine, less processed, closer in composition to the original material that condensed in the protoplanetary disk. This stratification, if it could be measured directly, would encode information about the duration of the comet's interstellar journey, about the intensity of cosmic ray exposure, about the balance between surface loss from sputtering and interior processing from radiation. But measuring this stratification requires accessing the interior either through natural fracturing or through deliberate excavation, neither of which is feasible for an object that will pass through the solar system once and never return. The surface alone is observable, and the surface is the most altered, the most processed, the least representative of primordial conditions. This is the frustration of studying interstellar comets. The parts most accessible to observation are the parts most contaminated by post-formation processes. The comet's path through the galaxy is not a straight line. The gravitational field of the Milky Way, shaped by hundreds of billions of stars and a massive dark matter halo, curves trajectories, creating orbits that bob up and down through the galactic disk. Stars themselves move in epicycles, small oscillations around their average circular motion, and the comet, not gravitationally bound to any particular star, follows a path influenced by the collective mass distribution of the galaxy over millions of years. This path may loop and curve, may carry the comet through regions of different stellar density, different radiation environments, different probabilities of close encounters with other objects. The probability of a direct collision with another interstellar object is vanishingly small. The interstellar medium, for all its atoms and molecules, is still overwhelmingly empty. The typical spacing between stars is measured in light years. The typical spacing between interstellar comets, if their population density is similar to the density inferred from detection rates, is measured in thousands or millions of astronomical units. Two such objects might share the same cubic parsec of space for millennia without ever approaching within 1 billion kilometers of each other. But gravitational perturbations need not involve close approaches. A distant passage near a star, at distances of thousands of AU where tidal forces are negligible, can still alter a comet's trajectory slightly, deflecting it by fractions of a degree, changing its velocity by meters per second. Accumulated over many such encounters, these small perturbations can add up, can randomize the comet's direction, can determine whether it eventually falls into a star system or remains adrift in the interstellar void indefinitely. 3I/Atlas's path brought it to the Sun. Whether by chance or by some prior perturbation that aimed it in this direction, the comet's trajectory intersected the solar system's gravitational sphere of influence, the region within which the Sun's gravity dominates over the galaxy's tidal field. Once captured by this influence, not captured into a bound orbit, but captured into an interaction that will significantly alter the trajectory, the comet's fate was determined. It would fall inward, accelerate under solar gravity, pass through perihelion, and be flung back out into interstellar space on a different heading. The new trajectory will carry the comet toward a different region of the galaxy. The deflection angle, determined by the hyperbolic orbit's geometry, is modest, perhaps 20 or 30 degrees. The comet's velocity, relative to the Sun at large distances, will be nearly unchanged, still about 17 kilometers per second, still consistent with the motion of a typical star in the solar neighborhood, but the direction is different, and direction matters over interstellar distances. A change of 20 degrees sustained over a journey of 1 million years translates to a lateral displacement of tens of parsecs, enough to carry the comet past different stars, through different molecular clouds, into different regions of the galactic disk. Where it will go is unknowable. The galaxy's gravitational field is chaotic on long time scales, sensitive to small perturbations, impossible to predict precisely over millions of years. The comet's future trajectory is a probability distribution, a cloud of possible paths spreading through phase space, any one of which is as likely as any other given the current uncertainties in position and velocity. It might pass through another stellar system in 100,000 years. It might drift through the interstellar medium for 1 billion years before the next close encounter. It might fragment, or collide with a molecular cloud and be disrupted, or be tidally torn apart by a close pass near a massive star, or it might continue, intact and inert, until the galaxy itself has evolved beyond recognition, until the Sun has exhausted its hydrogen and expanded into a red giant, until the Milky Way and Andromeda have merged into a single elliptical galaxy, until the universe has cooled and darkened and most stars have burned out. Comets are patient. They do not decay, except through the slow attrition of cosmic rays and impacts. They do not age in any biological sense. They simply persist, frozen archives drifting through time and space, waiting for the next moment of warmth, the next encounter with a star. Only the universe tracks such timescales. Only gravity and entropy remember the paths of individual comets across billions of years. For now, in this moment, 3I/Atlas moves through the outer solar system, sublimating gently, scattering light, offering its polarization signature to instruments on a small planet orbiting the star it is visiting. The moment is brief, the data is precious. The opportunity will not recur. Sunlight at the distance of 3I/Atlas delivers only a fraction of the energy that warms Earth. The inverse square law governs the dilution of radiation with distance, twice as far from the Sun, 1/4 the flux, 3 times as far, 1/9 at several astronomical units. The solar constant drops to a few percent of its terrestrial value, enough to sublimate the most volatile ices, but insufficient to drive the vigorous outgassing seen in comets that venture inside Earth's orbit. The warming is gentle, almost tentative, a gradual increase in photon flux that coaxes molecules from their frozen lattices without violence or sudden transformation. The nucleus itself does not warm uniformly. The surface, exposed to direct sunlight and to infrared radiation from the coma's gas and dust, heats faster than the interior, where ice remains insulated by layers of low-conductivity material. Thermal models suggest temperature gradients of tens of degrees over depths of meters, with the subsurface ice remaining near its initial temperature even as the surface bakes under solar illumination. These gradients create stresses. Ice expands and contracts with temperature changes, and different expansion rates at different depths can fracture the structure, opening new pathways for gas escape or sealing old ones as material shifts and settles. Cometary nuclei are not solid monoliths. Observations and theoretical models agree on this. Even if direct measurements of interstellar comets remain sparse, nuclei are porous, with voids and cracks and empty spaces making up 50% or more of their volume. This porosity is a consequence of formation by gentle accretion, by the sticking together of smaller particles under low-velocity collisions in a protoplanetary disk, a process that builds fluffy structures rather than compact ones. The voids are filled with gas when sublimation is active, with vacuum when it is not, and the flow of gas through this porous network determines where and how dust is entrained and ejected. The dust itself, the particles that populate the coma and create the polarization signature, originates from the nucleus surface and subsurface. As ice sublimates, it undermines the structural support of the dust grains mixed with it, and gravity, feeble at the nucleus's low mass but not entirely absent, combined with gas drag pulls or pushes the grains free. Some particles are small, submicron fragments of silicates or carbonaceous material, easily lifted by even weak gas flows. Others are larger, micron to millimeter-sized aggregates, requiring stronger flows or more favorable geometry to escape the nucleus's gravity well. Only took a few centuries of comet observations to realize that cometary dust spans an enormous size range, from nanometers to centimeters, with properties that vary continuously across that spectrum. The size distribution of particles in the coma is not the same as the size distribution in the nucleus. Larger particles, heavier and less responsive to gas drag, are preferentially retained or ejected at lower speeds, falling back to the surface or remaining in the inner coma. Smaller particles, with higher surface area to mass ratios, couple more efficiently to the gas flow and are accelerated to higher velocities, populating the outer coma and the dust tail. This differential ejection biases the observable dust population towards smaller sizes, and the polarization measurements, which are most sensitive to particles comparable in size to the wavelength of light, preferentially sample a specific window of the size distribution. The grains that scatter light most efficiently for polarimetry, those in the half-micron to few-micron range, are also the grains about which theory makes the most specific predictions. Mie scattering calculations, which treat particles as homogeneous spheres, provide a baseline for understanding how size and refractive index determine polarization as a function of phase angle. But real cometary dust is not homogeneous or spherical. Grains are irregular, often fractal aggregates of smaller subunits. They may have layered structures with refractory cores surrounded by ice mantles or organic coatings. They may be porous, with internal voids that lower the effective refractive index and alter scattering properties. All these complications make interpreting polarization data difficult. A measurement showing higher than expected polarization could indicate larger grains, or fluffier grains, or grains with different composition, or some combination of these factors. Disentangling the contributions requires additional constraints from other observables, color, which depends on grain size and composition, albedo, which depends on surface roughness and absorption, thermal emission, which depends on temperature and emissivity. Even with all these measurements, the inversion from observables to physical properties remains underdetermined, with multiple models fitting the data equally well. For 3I/Atlas, the polarization anomaly suggests something about the dust population that differs from typical solar system comets. The deeper negative polarization branch could indicate a higher fraction of large, irregular particles. The steeper slope in the positive branch could suggest fluffier aggregates with more internal porosity. The shifted inversion angle might reflect a different refractive index, implying different mineralogy or a different mix of silicates and organics, or it might reflect processing during the interstellar journey. Cosmic rays and UV photons can alter grain surfaces, creating radiation-damaged layers that change optical properties. Sputtering by interstellar hydrogen atoms can remove softer materials, leaving behind harder, more refractory components. The millions of years in interstellar space represent a post-formation evolution that solar system, comets, always shielded by the heliosphere, never experienced to the same degree. Testing these hypotheses requires more data, and more data requires more observing time, and observing time is a finite resource competed for by many worthy projects. The comet will not wait. It continues on its trajectory, brightening slowly as it approaches perihelion, but also becoming more difficult to observe as its position on the sky moves closer to the Sun from Earth's perspective. The window for optimal observations, when the phase angle is favorable and the comet is still far enough from the Sun to avoid daylight sky, narrows with each passing week. Telescopes around the world and in space coordinate their efforts. Optical polarimeters measure scattered light in visible wavelengths. Near-infrared spectrometers inventory molecular emissions. Radio telescopes detect carbon monoxide and other species that emit in millimeter wavelengths. Space-based UV instruments observe hydrogen Lyman alpha emission from the vast hydrogen coma that surrounds the comet, invisible from the ground but diagnostic of water production rates. Each instrument provides a different piece of the puzzle, a different constraint on the models, a different angle on the question of what this object is and where it came from. The data streams in, is reduced, is calibrated, is archived. Figures appear in preprints posted to online repositories, circulate among the community, spark discussions and follow-up observations and refinements. The anomaly in the polarization signature is confirmed by independent measurements from different telescopes. It is real, not an artifact of calibration or atmospheric effects or instrumental systematics. Something about the dust in this comet's coma genuinely differs from the canonical expectations. The difference is subtle. It is not a screaming contradiction, not a violation of known physics, not an indication of exotic chemistry or alien technology. It is a variation within the broad envelope of possible cometary properties, a hint that the conditions of formation or the history of evolution for this particular object deviate slightly from the norm established by solar system comets. Whether that deviation is significant, whether it tells us something fundamental about protoplanetary disks around other stars, or about interstellar processing, or about the diversity of outcomes in planet formation, remains an open question. Only time and more observations and deeper theoretical understanding will resolve it. Only the patient accumulation of data from many interstellar comets, when the sample size grows from a handful to dozens or hundreds, will reveal whether 3I/Atlas is an outlier or representative, whether its polarization signature is unique or common, whether the differences observed reflect fundamental variations in stellar nurseries or merely the stochastic scatter of individual formation histories. The comet does not know it is part of a sample. It does not know it is being compared and categorized and fitted into frameworks developed from studies of other objects. It simply is, and it simply scatters light. And the scattered light carries information whether or not anyone receives it. The solar wind, invisible and intangible, permeates the space through which the comet travels. This wind is not air, not atmosphere, but a stream of charged particles, mostly protons and electrons, ejected from the sun's corona at velocities ranging from 300 to 800 kilometers per second. The particles carry the sun's magnetic field with them, frozen into the plasma, dragged outward by the expansion, and stretched into a spiral pattern by the sun's rotation. This is the heliosphere, the bubble of solar influence that extends far beyond the orbits of the planets, out to the heliopause where the solar wind finally stalls against the pressure of the interstellar medium. 3I/Atlas. Entering this bubble from interstellar space, crosses a boundary that is not sharp but gradual, a transition region where the density and properties of the surrounding plasma shift from interstellar to solar in character. The comet itself, electrically neutral, does not respond to the magnetic fields or feel the solar wind's pressure directly, but the ionized component of its coma, the small fraction of molecules that have been stripped of electrons by solar UV or by collisions with other ions, does respond, and the interaction shapes the structure of the comet's plasma environment. As gas sublimates from the nucleus and expands into the coma, some fraction of the neutral molecules encounters UV photons energetic enough to ionize them. Water molecules lose an electron and become H2O plus ions. Carbon monoxide becomes CO plus. These ions, now charged, are picked up by the solar wind's magnetic field. The process is not gentle. The solar wind, moving at hundreds of kilometers per second, carries magnetic field lines that sweep over the ion, inducing electric fields that accelerate the newly ionized particle perpendicular to both the field and the wind direction. The ion begins to gyrate around the field line, its motion now coupled to the solar wind's motion, dragged away from the comet on a trajectory that diverges from the neutral molecules left behind. This mass loading, the addition of heavy cometary ions to the light solar wind plasma, creates a bow shock upstream of the comet, a standing wave in the plasma where the solar wind decelerates and heats and changes direction to flow around the obstacle, at close distances to the sun, where cometary activity is high and ion production rates are large. The bow shock is strong and well-defined, detectable by spacecraft instruments as an abrupt transition in magnetic field strength and plasma density. For 3I/Atlas, far from the sun and only weakly active. The shock is faint, perhaps barely formed. A subtle perturbation in the solar wind that might not even qualify as a discontinuity in the technical sense. Only took a few spacecraft missions to comets to measure both shocks directly and confirm what theory had predicted from fluid dynamics and plasma physics. Behind the bow shock, in the region between the shock and the comet, the plasma flow is slower and more turbulent. Magnetic field lines drape around the nucleus, forming a magnetotail that extends downstream, anti-sunward, shaped like an elongated teardrop. The ionized coma, confined by this draped field, flows down the tail at velocities intermediate between the neutral gas expansion speed and the solar wind speed, creating the ion tail visible in images of bright comets as a narrow, straight structure pointing away from the sun. For 3E/Atlas, the ion tail is faint, barely detectable except in long exposure images or in UV wavelengths where ion emissions are strongest. The tail extends for millions of kilometers, far beyond the visible coma, a ghostly streamer of plasma carried away by the solar wind. Within this tail, the ions undergo further reactions and dissociations, creating daughter species and ultimately being dispersed into the general solar wind population. Their cometary origin erased by mixing and dilution. The dust tail follows a different geometry. Dust particles, electrically neutral, do not respond to magnetic fields and are not carried by the solar wind. Instead, they are pushed by radiation pressure, the momentum carried by sunlight itself. Each photon that strikes a dust grain and is absorbed or scattered transfers a tiny amount of momentum to the grain, creating a force directed radially away from the sun. For small particles, this radiation pressure force can exceed the sun's gravitational attraction, and the grains are blown outward, accelerating as they move into regions of higher solar flux. The balance between radiation pressure and gravity depends on particle size. Small grains, with high surface area to mass ratios, feel stronger radiation pressure relative to gravity and are blown away rapidly. Large grains, with lower ratios, feel stronger gravity and are less efficiently expelled. This size-dependent force creates a curved dust tail, with smaller particles swept back more sharply and larger particles following trajectories closer to the comet's orbit. The curvature encodes information about the size distribution, and detailed modeling of tail morphology can constrain the range of particle sizes present in the coma. Observing the dust tail of 3I/Atlas requires subtracting the bright background of stars and the faint glow of zodiacal light, the scattered sunlight from interplanetary dust that fills the solar system. The tail itself is faint, a diffuse smudge barely above the noise level in images, detectable only through careful image processing and stacking of multiple exposures. Once detected, its shape can be measured, its curvature fitted to models, its implied size distribution compared with the polarization measurements to check for consistency. The two tails, ion and dust, extend in different directions, responding to different forces, tracing different populations of material ejected from the nucleus. The ion tail points radially away from the sun, modulo small deflections from magnetic field geometry and solar wind variability. The dust tail curves backward along the comet's orbital path, lagging behind the nucleus, its curvature depending on the particle's response to radiation pressure. In images, the two tails are often distinguishable by color. The ion tail appears blue due to emission from ionized carbon monoxide, while the dust tail appears yellowish-white from scattered sunlight. But for faint comets like 3I/Atlas, the color distinction is subtle and requires high-quality photometry to detect. The mass loss rate from the nucleus, the total amount of gas and dust leaving per second, can be estimated from the brightness of the coma and tails combined with models of sublimation physics and dust-to-gas ratios. For 3I/Atlas at its current distance, the mass loss rate is low, perhaps a few kilograms per second. Barely a whisper compared to the hundreds or thousands of kilograms per second seen in comets that approach within a few tenths of an AU from the Sun. Over the months of the comet's passage through the inner solar system, this steady trickle accumulates to tens or hundreds of metric tons of lost material, a small fraction of the nucleus's total mass, but enough to alter the surface appearance, to expose fresh layers, to change the dust population available for ejection. The lost mass disperses along the comet's orbit, forming a meteoroid stream that will persist for years, slowly spreading as orbital perturbations and radiation pressure modify the particle's trajectories. If Earth's orbit intersects this stream, meteors may result, though for an interstellar comet on a hyperbolic trajectory, the intersection is unlikely, and no meteor shower from 3I/Atlas is expected. The particles will simply continue on their own paths, some eventually falling into the Sun, others being ejected from the solar system by gravitational interactions with planets, a few perhaps being swept up by other bodies or accreting onto asteroids or being pulverized by mutual collisions in the distant future. Only the universe tracks the fate of individual dust grains across millions of years. Only entropy and statistics govern their eventual dispersal through the solar system and beyond. The comet itself, shedding mass but not structure, continues its journey. The tails grow and brighten slightly as perihelion approaches, then will fade as the comet recedes and sublimation decreases. The interaction with the solar wind will weaken, the bow shock will disappear, the ion tail will dissipate. The dust tail will persist longer, spreading and thinning, eventually becoming undetectable as the particles disperse and the surface brightness drops below observable limits. The comet will return to the darkness, to the interstellar medium, carrying slightly less mass than it arrived with, but otherwise unchanged in any fundamental way. The coma surrounding the nucleus extends far beyond what eyes alone could perceive. Even eyes far more sensitive than human vision, the visible coma, the cloud of dust and gas bright enough to scatter sunlight detectably, measures tens of thousands of kilometers across, a region within which the density of molecules, though vastly higher than in the surrounding space, remains lower than the best vacuum achieved in terrestrial laboratories. Beyond this visible boundary, the coma continues, thinning gradually, the density falling as molecules disperse and gas expands, but never reaching an absolute edge, never terminating in a well-defined surface. The hydrogen coma extends farthest. Water molecules, when they sublimate from the nucleus and flow into the coma, are photodissociated by solar UV radiation, breaking apart into hydrogen and hydroxyl radicals, the hydrogen atoms, extremely light and moving at high velocities imparted by the dissociation energy, escape the comet's weak gravity easily and form a vast cloud that can extend millions of kilometers, detectable only in Lyman alpha emission at ultraviolet wavelengths inaccessible from Earth's surface. Space telescopes observe this extended hydrogen cloud and use its brightness to infer water production rates, making assumptions about dissociation lifetimes and fluorescence efficiencies and the fraction of hydrogen that escapes versus being ionized or otherwise removed. For 3I/Atlas, the hydrogen coma is faint, consistent with low water production at its current distance from the Sun. Later, closer to perihelion, water sublimation will increase and the hydrogen cloud will grow, becoming the comet's most extended feature. Though still invisible to ground-based observers who lack access to UV wavelengths, the delicate geometry of gas and dust streaming from the nucleus follows patterns dictated by rotation, by the distribution of active regions on the surface, by the balance between solar heating and radiative cooling. Not all areas of the nucleus sublimate equally. Some regions, enriched in volatile ices or oriented favorably toward the Sun, outgas vigorously, creating jets that spray material into space in collimated streams. Other regions, mantled with thick layers of dust or depleted of near-surface volatiles, remain dormant, contributing little to the coma despite receiving similar solar illumination. This heterogeneity creates structure in the coma that persists for hours or days, visible as spirals or shells or localized enhancements in brightness when imaged with sufficient resolution and cadence. The spirals trace the rotation of active jets as the nucleus tumbles, each rotation sweeping a jet across different directions and creating a pattern that winds outward like water from a rotating sprinkler. The shells, sometimes called halos, form when sudden increases in activity release bursts of material that expand outward at constant velocity, creating expanding rings visible in time series imaging. For 3I/Atlas, such structures are difficult to detect. The coma is faint, and the resolution required to see spirals or shells at the comet's distance exceeds what most telescopes can achieve, except under the best observing conditions. A few images, taken with large apertures during excellent seeing, hint at asymmetries, at brightness variations that might indicate jet activity, but the detections are marginal, tentative, insufficient to map the active regions or constrain the rotation axis with confidence. Only took thousands of years of comet observations before humans developed instruments capable of resolving spatial structure in comae at distances of several AU. The molecules in the coma, freed from the solid phase and expanding into vacuum, carry kinetic energy derived from sublimation. The temperature of the nucleus surface, where ice transitions to gas, determines the initial velocity distribution of the escaping molecules. For water, sublimating at temperatures around 200 Kelvin, typical expansion velocities are near 1 km per second. For carbon monoxide sublimating at lower temperatures, velocities are somewhat higher, reflecting the molecule's lower mass and the Maxwell-Boltzmann distribution's dependence on temperature and molecular weight. These velocities, while modest compared to the orbital speeds of planets or the escape velocity from the Sun, are sufficient to carry molecules far from the nucleus before they are dissociated by sunlight or ionized by UV photons. The lifetimes of parent molecules, those ejected directly from the nucleus rather than produced by subsequent chemistry, vary by species. Water molecules survive for tens of thousands of seconds at 1 AU from the Sun, during which time they travel tens of thousands of kilometers. Carbon monoxide survives longer, being less susceptible to photodissociation. Hydrogen cyanide and methanol have intermediate lifetimes, their fates determined by the cross-sections for UV absorption and the flux of dissociating photons. As molecules fragment, daughter species appear, hydroxyl radicals from water dissociation, carbon atoms from carbon monoxide, CN radicals from hydrogen cyanide. These daughters have their own photochemical lifetimes and create secondary populations in the coma, spatially segregated from the parent molecules by the expansion and dissociation dynamics. Mapping the spatial distribution of parent versus daughter species provides constraints on gas expansion velocities and dissociation rates, which in turn inform models of coma chemistry and energy balance. Spectroscopy reveals these distributions by measuring emission line strengths as a function of position within the coma. A long slit spectrum, oriented across the coma, shows how the brightness of different emission lines varies with distance from the nucleus. Parent molecules are brightest near the center, where the density is highest and the time since ejection is shortest. Daughter species show broader distributions, peaking at larger distances where dissociation has had time to convert parents into fragments. For 3I/Atlas, such spatially resolved spectroscopy is challenging. The coma is faint, requiring long exposures, and the comet's motion across the sky during those exposures can smear the spatial information. Nevertheless, some observations attempt this measurement, using integral field spectrographs that capture spatial and spectral information simultaneously. building three-dimensional data cubes that can be sliced and analyzed to extract radial profiles of emission line brightness. The results, when they come, show profiles consistent with expectations for normal sublimation and photodissociation. The data do not reveal anything anomalous in the gas dynamics, no evidence for unusual expansion velocities or dissociation rates that would hint at exotic chemistry or unexpected energy sources. The gas behaves as gas should, expanding and fragmenting according to the physics understood from decades of cometry spectroscopy and from laboratory measurements of molecular cross-sections and lifetimes. This normalcy is itself informative. It suggests that whatever makes the polarization signature unusual, it is not reflected in the gas behavior. The anomaly lies in the dust, in the particles that scatter light, not in the molecules that emit it. The ice that sublimates appears ordinary in composition and behavior. The volatiles released match expectations for comets formed in cold protoplanetary disk environments. The chemistry proceeding in the coma follows familiar pathways, creating daughter species in proportions consistent with solar UV flux and molecular branching ratios measured in laboratories. Only the dust stands apart. Only the polarization signature hints at something different. This dichotomy, if it holds up under further scrutiny, narrows the range of explanations. Differences in gas composition or sublimation behavior can be ruled out. Differences in dust properties, size distribution, morphology, composition, porosity remain viable. The grains themselves, formed in the protoplanetary disk around another star, processed during millions of years in interstellar space, now being released into the coma of 3I/Atlas, carry the signature that distinguishes this comet from its solar system counterparts. Perhaps the grains are older. Solar system comets contain some fraction of pre-solar grains, tiny particles that condensed in the outflows of other stars before the Sun formed and were incorporated into the molecular cloud that collapsed to form the solar system. These grains, identified in meteorites and interplanetary dust particles by their anomalous isotopic compositions, represent a small contamination, a few parts per million of the total dust budget. But in an interstellar comet, the entire grain population could be pre-solar from the solar system's perspective, all of it formed around another star, none of it having passed through the Sun's protoplanetary disk. The isotopic compositions of these grains, if they could be measured, would reveal their origins. Oxygen isotopes, nitrogen isotopes, carbon isotopes, all carry signatures of the nucleosynthetic processes that created them, of the type of star that ejected the material, of the conditions in the stellar envelope or supernova ejector where condensation occurred. But measuring isotopes in comet dust requires either sample return, which is not feasible for an interstellar comet on a flyby trajectory, or high-resolution spectroscopy of emission lines from gaseous species, which does not probe the solid grains themselves. The grains remain characterized only by their collective optical properties, how they scatter light, how they absorb and emit thermal radiation, how their distribution affects the coma's brightness and color. These properties constrain but do not uniquely determine the grain's composition or structure. Multiple models, multiple scenarios, fit the available data equally well. The inversion problem, the challenge of inferring physical properties from remote observations, remains underconstrained and will likely remain so unless future interstellar comets are studied with more advanced techniques or unless theoretical understanding advances to the point where polarization signatures can be uniquely mapped to grain properties. The comet does not care about these ambiguities. It continues to sublimate, to eject dust, to populate its coma with grains that scatter sunlight and create the polarization signal that perplexes observers. The process is automatic, governed by thermodynamics and radiation pressure, and the mechanical properties of the nucleus structure. There is no intent, no awareness, No commentary offered on the questions raised by the measurements. Only photons carry information outward, and only instruments designed to receive them can decode the message. Incomplete and ambiguous as it is, the nucleus itself, the solid body at the heart of the coma, remains unresolved in images, a point source too small and too distant for its shape to be determined directly. Estimates of its size come from brightness measurements combined with assumptions about albedo, the fraction of incident sunlight reflected rather than absorbed. If the albedo is low, as expected for a heavily processed, carbon-rich surface, then a given brightness implies a larger nucleus. If the albedo is higher, the nucleus must be smaller to produce the same observed brightness. For 3I/Atlas, the albedo is assumed to be similar to other cometary nuclei, around 3 to 4%. Though this assumption is exactly that, an assumption, not a measurement, with this assumption, the brightness translates to an effective diameter of approximately 1 kilometer, with uncertainties spanning from several hundred meters to perhaps 2 kilometers, depending on the exact albedo and the nucleus's shape. A 1-kilometer comet is modest by solar system standards, smaller than many Jupiter family comets, larger than some of the tiny objects discovered in recent surveys, unremarkable in size but not insignificant. The mass, derived from the estimated volume and an assumed density, is even more uncertain. Cometary nuclei are porous, their bulk densities typically ranging from 300 to 600 kilograms per cubic meter, less dense than water ice despite being composed primarily of ice and rock. This low density reflects the high porosity, the voids and cracks that permeate the structure, remnants of the gentle accretion process that assembled the nucleus from smaller particles in the protoplanetary disk. For a 1-kilometer nucleus with density around 400 kilograms per cubic meter, the total mass would be a few hundred million metric tons, comparable to a small mountain on Earth, but distributed across a volume large enough to keep the surface gravity negligibly small. The escape velocity from such a body is measured in meters per second, far less than the expansion velocities of sublimating gas. Any molecule or dust grain ejected from the surface with even a modest velocity will escape the nucleus's gravity well and enter the coma, never to return. This makes cometary activity inherently wasteful. Nothing ejected is retained, nothing recycled. The nucleus can only lose mass, never gain it, except through the rare event of a collision with another object or the even rarer process of recapture of previously ejected material that has somehow lost enough energy to fall back. Only the slow accumulation of interstellar material during the millions of years between stellar encounters could add mass, and that accumulation is vanishingly small. Nanometers of deposited atoms and molecules over millions of years, negligible compared to the meters of material lost during a single passage near a star. The rotation of the nucleus, inferred from periodic variations in brightness as different surface regions rotate into and out of view, suggests a tumbling motion rather than a simple spin around a principal axis. The brightness changes are not sinusoidal, not the clean rise and fall expected from a smoothly rotating ellipsoid, but irregular, with multiple periodicities and amplitude variations that hint at complex rotational dynamics. This complexity could reflect an elongated shape, a highly irregular surface with large-scale topography, or a true tumbling state where the rotation axis itself precesses on timescales comparable to the rotation period. Tumbling is common among small solar system bodies, objects that are not perfectly rigid, that have internal friction or structural creep, can have their rotation perturbed by torques, gravitational, from asymmetric mass distribution, thermal, from asymmetric outgassing, collisional, from impacts that happened long ago and left the object spinning in a non-principal axis state. Once tumbling, an object can remain in that state for long periods, its rotation chaotic and difficult to predict precisely, its orientation at any given time requiring detailed numerical integration of the rotational equations of motion. For 3 I/Atlas, the exact rotation state remains uncertain. The brightness variations provide clues, but not definitive answers. The periodicity is roughly 8 hours, but the amplitude and shape of the light curve change from one rotation to the next in ways that are not easily explained by simple models. More data, collected over many rotation periods, would help constrain the shape and spin state, but the comet's faintness limits the cadence and signal-to-noise ratio of the observations, and the available data remains sparse and noisy. The surface composition, like the interior composition, cannot be measured directly but must be inferred from spectroscopic and photometric observations. The comet's color, measured by comparing brightness in different wavelength bands, is slightly red, consistent with the presence of organic compounds and radiation-processed carbon-rich material. The reddening is not extreme, not as pronounced as the ultra-red Kuiper Belt objects or some of the most primitive asteroids, but it is noticeable. A deviation from the neutral gray of fresh ice or unweathered silicates. Spectroscopic observations in the near-infrared, where many ice absorption features appear, show no strong bands attributable to water ice or other volatiles on the nucleus surface. This absence is expected. The surface is likely mantled with dust and refractory organics. The volatile ices buried beneath layers of non-volatile material left behind as sublimation removed the more easily vaporized components, only in freshly exposed regions. Perhaps on the walls of active pits or in recently fractured areas, would surface ice be directly visible, and such regions, if they exist, are too small to dominate the disk average spectrum of the unresolved nucleus. The thermal emission from the nucleus, measured at mid-infrared wavelengths, provides another constraint on surface properties. The temperature of the sunlit surface, determined by the balance between absorbed solar radiation and emitted thermal radiation, depends on albedo, thermal inertia, and surface roughness. Observations with infrared space telescopes detect a faint signal from 3 I/Atlas, consistent with a surface temperature of around 150 to 170 Kelvin. Colder than a bare icy surface would be at this distance, but warmer than the surrounding space, indicating active heating by sunlight and re-radiation at infrared wavelengths. The thermal inertia, a measure of how quickly the surface responds to changes in illumination, appears low, suggesting a surface covered with fine dust or porous material that insulates the underlying layers. High thermal inertia, characteristic of solid rock or ice, would lead to smaller temperature contrasts between sunlit and shadowed regions and between day and night. Low thermal inertia allows large contrasts, permits the surface to heat up quickly when illuminated and cool down quickly when shadowed, and is consistent with the regolith covered surfaces observed on cometary nuclei visited by spacecraft. No spacecraft will visit 3 I/Atlas, the comet's trajectory and timing, combined with the long lead times required to design and launch interplanetary missions, preclude any possibility of a flyby or rendezvous. The data collected will all be remote, all filtered through the limitations of distance and instrumentation and the inverse square law of radiation. What is learned about this comet will be learned from light alone, from photons that have bounced off its surface or scattered from its coma or been emitted by its molecules, carrying their small burdens of information across millions of kilometers to be captured by telescopes and decoded by humans. The light is faint, the signal is noisy, the interpretations are provisional, but the effort continues, driven by curiosity, by the desire to understand, by the recognition that opportunities like this are rare and fleeting and will not come again until another interstellar visitor happens to pass through the solar system, which might be months or years or decades from now. Only a few interstellar comets have been detected so far. Only a few more might be detected in the coming years if survey telescopes continue to scan the sky and algorithms continue to flag fast-moving objects on unbound orbits. The statistics of the interstellar comet population, their size distribution and composition and where they come from, remain poorly constrained based on a handful of examples and extrapolations that might or might not reflect reality. The nucleus of 3I/Atlas, small and dark and tumbling, carries no answers written on its surface. It simply is a remnant of another system's planet formation process, an accidental visitor to ours, a temporary target for observation before it recedes beyond detection and is lost to study forever. The grains drifting outward from the nucleus, carried by sublimating gas and pushed by radiation pressure, are not pristine samples of the material from which the comet formed. They have been altered, processed, subjected to environments and forces that change their properties over the billions of years since condensation in a protoplanetary disk around a star whose name and location are unknown and perhaps unknowable. In the original disk, grains formed through condensation of gas phase elements onto seed particles, building up layers of ice and refractory material as temperatures dropped and pressures allowed phase transitions. Silicate cores, perhaps, coated with water ice, carbon dioxide ice, carbon monoxide ice, methane, ammonia. Organic compounds synthesized in the gas phase or on grain surfaces through catalytic reactions. The exact sequence of condensation depended on the temperature gradient in the disk, on the local pressure, on the availability of elements whose abundances reflected the metallicity of the parent star and the prior history of the molecular cloud from which the system formed. These grains, once assembled, settled toward the disk mid-plane, collided gently with other grains, stuck together through electrostatic forces or frozen volatiles acting as glue, grew into larger aggregates. Some aggregates reached sizes where gravity began to matter, where mutual attraction could pull in more material and initiate runaway growth toward planetesimal formation. Others remained small, ejected from the system by gravitational interactions with nascent planets or scattered into distant orbits by close encounters or stellar flybys or turbulent motions in the disk. 3I/Atlas, or the material that became 3I/Atlas, was ejected. The exact mechanism is unknown. Could have been a gravitational slingshot around a giant planet. Could have been a close stellar encounter that stripped material from the outer disk. Could have been ejection during a period of violent, dynamical evolution when planets migrated and resonances swept through the system, rearranging orbits. Whatever the cause, the object was launched onto a hyperbolic trajectory relative to its birth star, sent into interstellar space with enough velocity to escape the system's gravity well and never return. Once in interstellar space, the processing began. Cosmic rays, arriving from all directions, penetrated the nucleus, depositing energy, breaking bonds, creating radicals that recombined into new molecules. The radiation dose accumulated over time, tens of millions of years, perhaps longer, until the total exposure exceeded anything experienced by solar system comets that formed at the same time but remained bound to the Sun, shielded by the heliosphere from the full intensity of galactic cosmic rays. The UV radiation field in interstellar space, though weak compared to the UV flux near a star, was persistent and unshielded. Photons from distant stars struck the nuclear surface, photodissociating molecules, creating a radiation-processed crust, enriched in complex organics and depleted in the most volatile species. The darkening proceeded slowly but inexorably. The surface albedo dropping as carbon-rich residues accumulated, as the reflective ices were converted into absorbing tars and kerogens. Only the interior remained relatively pristine, shielded by meters of overlying material from the most penetrating radiation. retaining a composition closer to the original disk condensates, but the interior is not directly observable, not accessible to remote sensing, not available for study unless the comet fragments and exposes fresh surfaces, or unless future analysis of ejected dust somehow samples material from depth. The dust grains now populating the coma of 3I/Atlas are drawn primarily from the processed outer layers. As ice sublimates, it undermines the structure, releasing grains that have spent millions of years at or near the surface, exposed to cosmic rays and UV photons, altered in ways that solar system comet dust, ejected from nuclei that spent their lives in the heliosphere, has not been. This alteration might account for the polarization anomaly. Radiation processing can change the optical constants of organic materials, altering their refractive indices, their absorption coefficients, their scattering properties. Cosmic ray bombardment can create structural damage, vacancies and dislocations in crystalline lattices, amorphization of initially ordered structures, changes in porosity and density. These modifications, accumulated over millions of years, could shift the polarization signature in the directions observed. Deeper negative branch, steeper positive slope, altered inversion angle. Testing this hypothesis requires laboratory experiments, simulating interstellar radiation environments, and measuring the optical properties of processed samples. Some such experiments have been performed, irradiating ice and organic mixtures with UV photons or ion beams, measuring the resulting spectra and scattering properties. The results show that processing indeed changes optical properties, but the exact changes depend sensitively on the initial composition, the radiation dose, the temperature during irradiation, and other factors that are difficult to constrain for an interstellar comet whose history is unknown. The models, therefore, remain uncertain. They can reproduce the observed polarization signature under certain assumptions about grain composition and processing history, but other models, with different assumptions, can also fit the data. The degeneracy persists, the inversion problem remains under-constrained, and the anomaly, while confirmed and real, does not yet yield a unique explanation. Only more data from more interstellar comets will break the degeneracy. Only the accumulation of a statistical sample, objects with different polarization signatures that correlate or don't correlate with other observables, will reveal the patterns that single object studies cannot resolve. The comparison with 2I/Borisov, the second interstellar comet discovered and the first to be studied extensively, offers some clues. Borisov's polarization signature, measured at multiple phase angles, appeared largely consistent with solar system comets, showing no strong anomalies, no deviations that suggested unusual dust properties. This difference between 2I/Borisov and 3I/Atlas might indicate that interstellar comets are not a homogeneous population, that their properties vary depending on formation conditions or interstellar processing histories, or simply stochastic variations in initial composition. Or it might indicate that the measurements of Borisov were not precise enough to detect subtle anomalies, or that the phase angle coverage was insufficient to reveal features in the polarization curve that only appear at specific geometries. The uncertainties are large, the sample size is small, and firm conclusions remain elusive. Only took a century of modern astronomy to detect the first interstellar objects, only a few years since then to find 3 more. Only a matter of time before the catalogue expands and comparative studies become meaningful. The grains themselves, the individual particles scattering the light and creating the polarization signature, are diverse. Some are submicron silicates, magnesium-rich or iron-rich, crystalline or amorphous. Depending on the thermal history of the disk where they condensed, some are carbonaceous, organic-rich, ranging from simple aliphatic hydrocarbons to complex polycyclic aromatic structures, from amorphous carbon to graphitic or even diamond-like phases if pressures and temperatures during formation allowed such condensation. Some grains are aggregates, fluffy structures composed of smaller subunits held together by weak forces, porous and fragile, easily disrupted by collisions or thermal stress. Others are more compact, solid particles with higher densities and greater structural integrity, resistant to fragmentation and capable of surviving the stresses of ejection and transport through the coma. The size distribution spans orders of magnitude, from nanometers to millimeters, with each size range contributing differently to the polarization signature. The smallest grains, those much smaller than the wavelength of light, scatter inefficiently and contribute little. The largest grains, those much larger than the wavelength, scatter in the geometric optics regime and also contribute less to polarization. The intermediate sizes, those comparable to the wavelength, roughly half a micron to a few microns for visible light, dominate the polarization signal and are thus the grains about which the measurements provide the most information. But even within this size range, the properties vary. Shape varies. Some grains are spherical or nearly so, others elongated, still others irregular and fractal. Composition varies. Some grains are pure silicates, others pure organics. Many are mixtures, intimate or layered. Porosity varies. Some grains are solid, others are sponge-like, filled with voids that reduce the effective density and alter the refractive index. All this diversity is collapsed into a few numbers: the degree of polarization, the inversion angle, the slope. The richness of the grain population is compressed into a sparse set of observables, and the challenge is to infer the diversity from the compression, to reconstruct the population from its average signature, to learn about individual grains from the collective scattering of millions of them. The task is difficult, perhaps impossible in any complete sense, but progress is made. Constraints are placed. Hypotheses are tested and refined. The grains do not reveal themselves fully, but they reveal enough to guide the next observations, to inform the next models, to narrow the range of possibilities and push understanding incrementally forward. The negative polarization branch. That peculiar regime where scattered light is polarized perpendicular to the scattering plane rather than parallel to it, has puzzled researchers since its first detection in comets decades ago. The effect is counterintuitive. Simple scattering theory, applied to spherical particles, predicts positive polarization at all phase angles except near 0 degrees. Yet observations consistently show negative polarization at small phase angles for most atmosphereless solar system bodies, comets, asteroids, planetary satellites with dusty surfaces. The explanation involves multiple scattering and coherent backscattering, processes where photons interact with particles more than once, or where scattered waves interfere constructively in the backward direction. These effects become important when particles are closely spaced or when surfaces are rough on scales comparable to the wavelength of light. The resulting polarization is negative, meaning the electric field oscillates preferentially perpendicular to the scattering plane, and the depth of the negative branch, how negative the polarization becomes, depends on the properties of the scattering medium. For 3I/Atlas, the negative branch is deeper than typical. This suggests either a higher density of scatterers in the coma, which seems unlikely given the low activity level, or particles with surface properties that enhance coherent backscattering, such as greater roughness or more complex internal structure. Fluffy aggregates, with sub-wavelength voids and irregular surfaces, can produce strong negative polarization through multiple internal scattering within the aggregate structure, each scattering event contributing to the coherent backscatter component. Another possibility involves the size distribution extending to larger particles than typical. Large particles, those several wavelengths across, can exhibit negative polarization through geometric effects and shadow hiding, where the particle's shadow on itself at small phase angles creates asymmetries in the scattered light distribution. If the dust in 3I/Atlas's coma contains a higher fraction of large particles, perhaps because the gas drag during ejection was weaker or the nucleus surface has a different size distribution of regolith, the negative branch would deepen accordingly. Only decades of laboratory measurements on cosmic dust analogues and detailed modeling of light scattering by irregular particles have brought understanding to this level. Only numerical simulations, calculating scattering from millions of randomly oriented particles with complex shapes, can reproduce the observed polarization curves and connect them to physical properties. The inversion angle, the phase angle where polarization crosses from negative to positive, sits around 25 degrees for 3I/Atlas, shifted from the canonical 20 degrees observed for most solar system comets. This shift is small, a few degrees, but significant given the precision of the measurements. The inversion angle correlates empirically with other properties, albedo, color, size distribution, and its value places 3I/Atlas in a parameter space slightly offset from the main population of comets observed to date. Why this shift occurs is not fully clear. Theories link the inversion angle to the refractive index of the scattering particles. Higher refractive indices pushing the inversion angle to larger phase angles. Organics generally have lower refractive indices than silicates, so a composition richer in silicates would shift the inversion angle upward. But the shift could also reflect differences in porosity, in the mixing of materials within grains, in the presence of ice mantles that modify the effective refractive index, or in the size distribution affecting where the transition from negative to positive scattering dominates. The models can accommodate all these possibilities. They can fit the data by adjusting parameters within plausible ranges. What they cannot do, without additional constraints, is identify which parameters are actually responsible, which physical properties are truly different in 3I/Atlas compared to solar system comets. The observations point to differences, but do not specify their nature precisely. The positive branch, the regime at larger phase angles where polarization is positive and increases with phase angle before reaching a maximum and declining, provides additional information. The slope of this branch, quantified as the rate of change of polarization with phase angle, is steeper for 3I/Atlas than for most comets. Empirically, steeper slopes correlate with larger grains or with grains that have higher porosity and lower effective refractive indices. If the slope indicates larger grains, then the dust population in 3Y/Atlas's coma is skewed toward larger sizes compared to typical comets. This could result from the nucleus surface having been processed over millions of years in interstellar space, with smaller grains preferentially removed by sputtering or sublimation of ice binders, leaving behind a lag deposit enriched in larger, more robust particles. When these particles are finally ejected by sublimating volatiles, they populate the coma with a size distribution that differs from the distribution in freshly formed or less processed comets. If the slope indicates higher porosity, then the grains are fluffier, more fractal, with more internal voids. Such structures are expected for grains that grew by coagulation in protoplanetary disks, sticking together gently without compacting into solid masses. Solar system comets also show evidence for fluffy grains. But if the grains in 3I/Atlas are even fluffier, perhaps because the disk where they formed had lower collision velocities or different turbulence properties, the polarization slope would steepen accordingly. Disentangling size from porosity from refractive index requires combining polarization measurements with other observables. Thermal emission provides constraints on albedo and size distribution through modeling of infrared spectral energy distributions, spectropolarimetry. Measuring polarization as a function of wavelength rather than just at a few discrete wavelengths provides additional leverage by revealing how polarization varies with the ratio of particle size to wavelength. Observations at millimeter or radio wavelengths, where emission comes from larger particles, can constrain the size distribution at the large end, where optical and infrared observations become insensitive. Some of these additional observations have been attempted for 3I/Atlas, though the faintness of the comet limits what can be achieved. Thermal infrared measurements with space telescopes detect a signal, but the signal-to-noise is low, and the derived size distribution has large uncertainties. Spectropolarimetry is planned but challenging, requiring long integrations and careful calibration to separate the small polarization signal from instrumental effects and sky background. Radio observations have not detected the comet, placing only upper limits on the emission from large particles or from molecular lines, limits that are not very constraining given the low activity level. The data, therefore, remains sparse. The polarization anomaly is confirmed, but its interpretation is not unique. Multiple models fit, multiple explanations are plausible, and without additional constraints or additional interstellar comets for comparison. The ambiguity persists. Only patience and continued observation will resolve it, only the accumulation of more data from this comet and from future interstellar visitors will narrow the possibilities and reveal whether the anomaly is a clue to fundamental differences in dust properties or merely an indication of natural diversity within a broader population. The comet continues its path, indifferent to the uncertainty it creates, scattering light according to the properties of its dust, offering its polarization signature to anyone equipped to measure it. The signature is unexpected, but the comet has no expectations. It simply is, and the light it scatters simply carries the information it carries, whether or not that information is fully understood. Comparisons with solar system objects reveal both similarities and subtle distinctions. The broad population of comets observed from Earth shows a range of polarization behaviors, clustering around average values, but with scatter that reflects the diversity of formation conditions, dynamical histories, and current activity levels. Jupiter family comets, short-period objects originating from the Kuiper belt and now orbiting in the inner solar system, tend to show one set of characteristics. Long-period comets, arriving from the Oort cloud on their first or few passages near the Sun, show somewhat different properties. Though the trends are not always clear or statistically robust given the limited sample sizes, 3I/Atlas falls outside both populations by virtue of its origin, but shares characteristics with each. Its polarization curve resembles long-period comets in some respects, the steeper slope. The slightly shifted inversion angle, but differs in the depth of the negative branch, which exceeds what most long-period comets display. This partial resemblance suggests shared formation mechanisms or evolutionary paths, while the differences hint at the variations introduced by interstellar processing or by the particular conditions in the comet's birth environment. Kuiper belt objects, the small icy bodies beyond Neptune that never or rarely visit the inner solar system, provide another comparison. Those few that have been studied photometrically and spectroscopically show surfaces enriched in organics and processed ices, darkened by radiation over billions of years. Their colors are often red, indicating complex organic chemistry. Their albedos are low, sometimes even lower than cometary nuclei, reflecting the absence of fresh ice exposure. 3I/Atlas, having spent millions of years in interstellar space under similar radiation conditions, might have developed surface properties convergent with Kuiper belt objects, despite forming around a different star. Testing this hypothesis requires spectroscopic data that can reveal surface composition directly, but such data is difficult to obtain for a faint, unresolved object like 3I/Atlas. The spectrum shows reflected sunlight, not emission lines or absorption bands strong enough to identify specific minerals or organic compounds unambiguously. The color is slightly red, consistent with organics, but not diagnostic. The lack of strong ice absorption bands suggests a dust-mantled surface, but this is expected and not unique to interstellar comets, only a direct sample, brought to Earth by a sample return mission, could definitively reveal the composition and structure of the grains. But no such mission is possible for an object on a one-time flyby trajectory through the solar system. The data will remain remote, the interpretations indirect, the conclusions provisional. Some researchers propose that future missions could target interstellar comets, if detected early enough in their approach and if propulsion technology advances sufficiently to enable fast intercepts. A spacecraft launched on a trajectory to rendezvous with an incoming interstellar object could carry instruments to analyze the coma, image the nucleus at high resolution, measure the composition of ejected dust and gas, perhaps even land on the surface or collect samples for return. Such a mission would transform our understanding, replacing inference with direct measurement, ambiguity with certainty, but such missions are years or decades away, requiring technologies not yet developed and funding not yet allocated. For now, and for the foreseeable future. The study of interstellar comets relies on telescopes, on photons, on the patient work of extracting information from faint signals against noisy backgrounds. The comparison with 1I/Oumuamua, the first confirmed interstellar object discovered in 2017, offers little help in understanding 3I/Atlas. Oumuamua showed no detectable cometary activity, no coma, no tail, no evidence for sublimation despite passing well inside Earth's orbit where solar heating should have triggered outgassing if volatile ices were present near the surface. Its nature remains debated, perhaps a comet with a thick, non-volatile crust preventing gas escape, perhaps an asteroid, perhaps something more exotic. Its rotation was complex, possibly tumbling, and its shape, inferred from light curve variations, appeared highly elongated. A cigar or pancake unlike any solar system object observed previously, 3I/Atlas, by contrast, is clearly active, clearly sublimating, clearly producing a coma and exhibiting cometary behavior. In this sense, it resembles 2I/Borisov more closely than Oumuamua, confirming that active comets from other stellar systems do exist and do behave, at least broadly. As solar system comets behave, the differences are in the details, in the polarization signature, in the subtle deviations from canonical behavior that suggest variations in dust properties rather than fundamental differences in physics. Only 3 interstellar objects with confirmed activity or clear cometary characteristics have been studied, only 3 data points from which to draw conclusions about the population as a whole. The statistics are poor, the uncertainties large, the generalizations premature. Each new detection adds to the sample, narrows the uncertainties, refines the understanding. But the pace is slow, limited by the rarity of interstellar visitors passing close enough to the Sun to be detected and bright enough to be studied in detail. The detectability of interstellar comets depends on their size, their albedo, their distance from the Sun when discovered, and the sensitivity and sky coverage of the surveys searching for them. Current surveys, designed primarily to find near-Earth asteroids and potentially hazardous objects, detect interstellar comets as a byproduct, flagging objects with unusual velocities or unbound orbits for follow-up observation. As survey capabilities improve, larger telescopes, wider fields of view, more frequent cadence, the detection rate should increase, revealing more interstellar visitors and building the statistical sample needed to understand the population. Projections suggest that 1 or 2 interstellar comets might be detected per year with next-generation survey telescopes, Systems like the Vera Rubin Observatory that will scan the entire visible sky every few nights and detect objects down to fainter magnitudes than current surveys achieve. With such detection rates, a meaningful sample could accumulate within a decade, enough objects to identify trends, correlations, subpopulations, to test hypotheses about formation mechanisms and interstellar processing and the diversity of planetary systems across the galaxy. But even with dozens of detections, the challenges of detailed study remain. Most interstellar comets will be faint, discovered late in their approach or already receding, with limited time for follow-up observation. Only a small fraction will pass close enough to the Sun and be discovered early enough to allow extensive monitoring across multiple wavelengths and geometries. The data will remain sparse, the interpretations uncertain, the questions numerous. 3I/Atlas represents one of the better studied cases, discovered relatively early, observable over several months, accessible to multiple telescopes and techniques. Yet even with this attention, the polarization anomaly resists definitive explanation. The dust properties remain ambiguous. The origin and history of the comet are constrained only loosely. The object came from somewhere in the galaxy, from a stellar system with properties that can be guessed at but not known, carrying grains that formed billions of years ago in a disk whose characteristics can be modeled but not measured. The grains scatter light. The light carries a signature. The signature is unexpected. This much is certain. The rest is interpretation, hypothesis, models that fit the data within uncertainties but do not compel belief, do not close the door on alternatives, do not answer all the questions they raise. Only the comet knows its own story, and the comet does not speak in words or equations or explanations. It speaks only through the photons it scatters, through the molecules it releases, through the faint signals captured by instruments operated by humans trying to understand something that formed elsewhere, that traveled farther than any human will ever travel, that visited briefly and will depart forever. The effort continues. More observations are scheduled, more data is collected, more papers are written and published and read and cited. The polarization curve is refined, the uncertainties narrowed, the models updated. The comet fades as it recedes from the Sun. The coma thins, the activity declines. Within months, it will be too faint for detailed study. Within a year, it will be undetectable except as a faint point of light in the largest telescope's deepest images. Within a few years, it will be gone entirely from observational reach, returning to the interstellar medium from which it came. The data will persist. The anomaly will remain in the archives, in the published literature, in the collective knowledge of the scientific community. Future researchers, studying future interstellar comets, will return to 3I/Atlas for comparison, will cite its polarization signature as a point of reference, will wonder whether the next object will show similar deviations or whether 3I/Atlas was unique, an outlier, an exception rather than a representative. Only time will tell. Only the continued accumulation of observations, the patient work of science proceeding incrementally, will reveal the patterns hidden in the diversity, the rules governing the exceptions. The framework that can accommodate both 3I/Atlas and 2I/Borisov and Oumuamua and all the interstellar objects yet to be discovered. The comet does not wait for these answers. It continues outward, crossing planetary orbits in reverse order from its inward journey, passing Mars's orbit, approaching Earth's, continuing toward Venus and Mercury, though it will not come close to either. The trajectory is determined. The path calculable from the current position and velocity and the Sun's gravitational field. No surprises are expected. No sudden changes in direction or speed except the minuscule perturbations from outgassing and radiation pressure. The light scattered from the coma grows fainter each day. the signal dropping as the square of the distance, requiring longer exposures, larger apertures, better seeing conditions to maintain adequate signal to noise. The observers compete with weather, with telescope schedules, with the moon's phase and position, with the creeping advance of twilight as the comet's elongation from the sun decreases. Every clear night is precious. Every successful observation, a small victory against the constraints of time and geometry and instrumental capability. The dust grains, still being ejected from the nucleus, still scattering sunlight, still creating the polarization signature that marks this comet as unusual, drift outward into the coma and beyond, into the tail, eventually dispersing into interplanetary space where they will remain, spreading slowly, mixing with the zodiacal dust cloud, becoming indistinguishable from the general background of particles that fill the solar system. Some grains will fall into the sun, spiraling inward under the pointing Robertson effect, the subtle radiation drag that robs them of angular momentum. Others will be ejected by radiation pressure or planetary gravitational assists, leaving the solar system on their own hyperbolic trajectories, returning to interstellar space as their parent comet does. Only entropy tracks the dispersal. Only statistics governs the eventual fate of each grain. Fragmentation remains a possibility, a concern among those monitoring the comet's evolution. Cometary nuclei are fragile, held together by weak forces, susceptible to fracturing under thermal stress or rotational instability or structural failure as internal voids collapse. Many comets have been observed to split during or after perihelion passage, separating into multiple fragments that follow slightly different trajectories, each creating its own small coma, each fading as their limited mass sublimates away over weeks or months. For 3 Ice/Atlas, the stresses are lower than for comets that approach the sun closely. The temperature gradients are modest, the rotational forces weak given the slow rotation rate and low mass. But millions of years in interstellar space may have weakened the structure. Cosmic ray damage creating microfractures, thermal cycling between warmer and colder interstellar environments causing expansion and contraction that fatigue the material. A nucleus that appears stable might be riddled with cracks, held together by compression or by frozen volatiles that act as glue but ready to separate when sublimation removes the binding material. Observers watch for signs of fragmentation, sudden changes in brightness, the appearance of multiple condensations in the coma, asymmetries in the dust distribution that would indicate discrete sources rather than a single nucleus. So far, no such signs have appeared. The comet appears intact, its light curve variations consistent with rotation and changing viewing geometry. Its coma morphology unremarkable, but the possibility persists, and each new set of observations includes a check for fragmentation, a comparison with previous images to detect any changes that might indicate structural failure. If fragmentation occurs, it would complicate the interpretation of the polarization data. Multiple nuclei would mean multiple sources of dust, potentially with different size distributions or compositions if the fragments sample different regions of the original nucleus with different processing histories. The combined polarization signature would be a mixture, a weighted average that might not represent any single fragment accurately. Understanding what caused the anomaly would become more difficult. The signal diluted and confused by the multiplicity of sources. But fragmentation would also offer opportunities. Fragments expose fresh surfaces, interior material that has not been processed by interstellar radiation, ice and dust closer in composition to the primordial material from which the comet formed. Observing such fresh material could provide constraints on the interior composition, on the stratification between processed crust and pristine core, on the extent to which cosmic rays penetrated and altered the bulk composition versus only the outermost layers. Only a few comets have fragmented at distances far enough from the Sun for the fragments to be studied in detail before sublimation erased the evidence. Most fragmentations occur near perihelion, where thermal stress is maximum, and the fragments sublimate rapidly, fading within days or weeks. A fragmentation at several ATM, or where temperatures are low and sublimation rates modest, would allow longer-term monitoring. A rare opportunity to study cometary interiors and structural properties directly. 3. I/Atlas shows no signs of imminent fragmentation, but the possibility is noted. The observations continue. The data is examined for any hints of change. The comet remains whole, at least for now, continuing its journey without apparent distress. The structural integrity of the nucleus depends on its composition and porosity and the strength of the bonds holding the material together. Ice, even at the low temperatures of the outer solar system, has some structural strength, able to bear weight and resist deformation over short time scales. But ice creeps under stress, deforming slowly, relaxing strains over days or months or years. A nucleus composed primarily of ice, with only a minor fraction of dust and refractory material, would be relatively weak, susceptible to tidal disruption if it passed close to a massive body, or to rotational breakup if spun too fast. A nucleus with a higher dust-to-ice ratio, with silicate and organic grains forming a matrix reinforced by frozen volatiles, would be stronger, more resistant to fragmentation, better able to survive the stresses of thermal cycling and rotation and collisions with other objects. The exact ratio in 3I/Atlas is unknown, inferred only from the observed dust-to-gas production ratio in the coma, which itself is uncertain and may not reflect the bulk nucleus composition if different regions have different ice contents, or if sublimation preferentially removes ice versus dust. Measurements of coma brightness and molecular emission lines suggest a dust-to-gas ratio by mass of order 1, meaning roughly equal amounts of dust and gas are being ejected. This ratio is typical for comets, neither particularly dust-rich nor gas-rich, and implies a nucleus composition that is also typical. A mixture of ice and refractory material in proportions similar to what is inferred for solar system comets. But the uncertainties are large, factors of 2 or more, and the ratio may change as different regions of the nucleus rotate into view or as the comet approaches or recedes from the Sun and sublimation rates vary. Only direct measurement of the nucleus's density and strength, which would require a spacecraft landing or impact experiment, could provide definitive constraints on structural properties. Such measurements exist for a few solar system comets visited by spacecraft, revealing nuclei with densities around 400 kilograms per cubic meter and tensile strengths weaker than fresh snow. Barely able to resist forces that would be trivial on Earth, but sufficient to hold together under the weak self-gravity of a kilometer-sized body. 3I/Atlas likely has similar properties, formed by similar processes even if in a different stellar system. The physics of coagulation and accretion in protoplanetary disks does not depend strongly on which star is at the center, and the resulting objects should have similar structures and strengths unless the disk conditions differ dramatically in temperature or turbulence or composition. The millions of years in interstellar space may have weakened the structure slightly, cosmic ray damage creating defects, but the overall properties probably remain within the range observed for solar system comets. The rotation rate, measured at roughly 8 hours per period, is slow enough to avoid rotational instability. The centrifugal force at the equator of a 1-kilometer body rotating with this period is tiny, far smaller than the self-gravity, posing no risk of shedding material or breaking apart from spin-up. If the comet were to fragment, rotation would not be the cause. Thermal stress or structural weakness or a pre-existing fracture would be more likely culprits. Observations continue. Monitoring continues. The possibility is acknowledged, but no evidence supports it. The comet appears stable, continuing on its trajectory without incident, sublimating steadily, scattering light, offering its polarization signature to telescopes that track it across the sky. The nucleus remains intact. The coma remains coherent. The tail extends smoothly without the discontinuities or multiple streamers that would indicate fragmentation or discrete jets from separated nuclei. Only time will reveal whether the structure holds or fails. Only the comet itself, through its behavior or its breakup, will demonstrate its strength or fragility. For now, it endures. A small icy body held together by forces that, while weak by terrestrial standards, suffice to resist the gentle stresses of its current environment. The brief window of visibility narrows with each passing week. The comet, moving on its hyperbolic trajectory, approaches perihelion, the point of closest approach to the Sun, at a distance that will place it beyond Earth's orbit, far enough that solar heating remains modest, and activity never reaches the levels seen in comets that venture inside 1 AU. This distant perihelion is both a limitation and a blessing. Limited because the comet remains faint and difficult to observe. Blessing because it retains more of its primordial character, less altered by the violence of close solar approach. The date of perihelion is calculable with high precision from the orbit, determined by tracking the comet's position over many nights and fitting the observations to a hyperbolic trajectory. The precision is remarkable. Uncertainties of only minutes in the timing, despite the comet being millions of kilometers away and moving through a gravitational field perturbed slightly by planets and solar wind pressure and outgassing forces. The mathematics of celestial mechanics, refined over centuries, predicts where the comet will be at any future time with accuracy that would have seemed miraculous to earlier generations of astronomers. After perihelion, the comet will recede, moving away from the Sun on the outbound leg of its hyperbola, velocity decreasing slightly as solar gravity pulls backward, but never enough to reverse the motion, never enough to capture the comet into a bound orbit. The asymptotic velocity, the speed the comet will approach at large distances as solar gravity becomes negligible, is determined by the orbital energy, by the sum of kinetic and potential energy at any point along the trajectory. For 3I/Atlas, this asymptotic velocity is similar to the incoming velocity, modified only by the change in direction from the gravitational deflection. The comet will leave the solar system on a heading different from its arrival, the trajectory bent by the Sun's gravity through an angle determined by the perihelion distance and the velocity. The deflection is modest, a few tens of degrees, enough to send the comet toward a different region of the galaxy, but not enough to reverse its direction or alter its speed dramatically. Within a few years, the comet will cross the orbit of Neptune, moving outward through the Kuiper Belt region, passing through the scattered disk and eventually exiting the heliosphere into interstellar space. Only the heliosphere's outer boundary, the heliopause where the solar wind stalls against interstellar pressure, marks the transition back to the environment the comet has known for most of its existence. Beyond that boundary, the solar wind's influence fades, the galactic cosmic ray flux increases, the interstellar magnetic field and neutral gas dominate the environment. The comet will return to the conditions it experienced during its millions of years of travel before encountering the Sun, drifting through the galaxy, accumulating radiation damage, cooling toward equilibrium with the cosmic microwave background, becoming once again just another small, icy body in the vast spaces between stars. The observations that captured the comet's brief passage through the inner solar system will persist long after the comet itself has faded from view. The data archived, the images stored, the spectra and polarization measurements preserved in digital form, accessible to future researchers who may find new ways to analyze them, new techniques to extract information, new theories against which to test the observations. The comet itself will be gone, beyond reach, but its legacy in the data will endure. Future interstellar comets will be compared to 3I/Atlas, their polarization signatures measured and plotted against the curve established here, their properties evaluated in the context of what was learned from this object. some future comet may show a similar anomaly, confirming that the unusual polarization signature is not unique but represents a class of objects or a type of processing. Another may show normal polarization, placing 3I/Atlas as an outlier, an exception requiring special explanation. The pattern will emerge only with time, with sample size, with the patient accumulation of data from many objects. Only then will the significance of the anomaly become clear. Only then will it be possible to say whether 3I/Atlas taught us something fundamental about interstellar comets or whether it was merely a curiosity. An interesting case, but not representative. A single data point in a distribution too broad to characterize from one example. The question of what the polarization signature implies about the comet's birth environment remains open. If the dust properties truly differ from solar system comets, the difference might trace back to the protoplanetary disk where the comet formed. Different stellar metallicities produce different abundances of elements available for dust condensation. A star richer in carbon might produce more carbonaceous grains, changing the refractive index and thus the polarization properties. A star poorer in oxygen might have different silicate to organic ratios, again affecting the dust characteristics. Or the difference might arise from disk dynamics. Turbulence in the disk affects grain growth and coagulation, determining whether dust remains small and compact or grows into large fluffy aggregates. Temperature gradients determine which volatiles condense at which locations, setting the ice composition and the distribution of ice mantles on refractory cores. Radiation fields from the central star or nearby massive stars affect photochemistry, determining which organic molecules form and survive to be incorporated into cometary ice. All these factors vary from system to system, from disk to disk, creating diversity in the properties of the comets and planetesimals that form. The challenge is to connect the observed polarization signature, a sparse set of numbers, to the complex multidimensional parameter space of disk properties, an inversion problem that is wildly under-constrained without additional observables or without a large sample to establish correlations. Theoretical models of protoplanetary disks have advanced significantly in recent years, incorporating more realistic physics, more detailed chemistry, more sophisticated treatments of turbulence and magnetic fields and radiative transfer. These models can predict, at least in principle, how dust properties should depend on disk conditions, how size distributions and compositions and porosities should vary with location in the disk and with time as the disk evolves. Comparing these predictions to observations of interstellar comets could, eventually, provide constraints on disk properties in other stellar systems, revealing whether the diversity seen in exoplanet systems extends to the comets and small bodies as well. But this vision remains aspirational. The current data is insufficient, the models still too uncertain, the connections between theory and observation still too loose. Progress will come incrementally, with better observations of more objects, with refined models tested against expanding datasets, with cross-disciplinary collaborations bringing together expertise in comet science, protoplanetary disk physics, dust optics, and observational techniques. 3I/Atlas contributes one small piece to this larger puzzle. Its polarization signature, unexpected and not yet fully explained, adds to the evidence that interstellar comets carry information about their origins, that they are not all identical, that studying them reveals diversity that reflects the diversity of planetary systems and stellar nurseries across the galaxy. The comet itself may not provide definitive answers, but it asks questions. It challenges assumptions. It pushes the field forward by demonstrating that there is more to learn, more to discover, more complexity than simple extrapolations from solar system comets would suggest. Only the continued effort, the sustained attention to these rare visitors, will unlock the information they carry. Only the combination of observations and theory and patient analysis will translate the faint signals into understanding. The comet recedes, the signal fades, the opportunity passes, but the data remains. And with it, the possibility that someday, someone will look at the polarization curve of 3Y/Atlas and see not an anomaly, but a piece of a larger pattern. A key to understanding something fundamental about how planetary systems form and evolve and scatter their debris into the galaxy. The implications extend beyond this single comet, beyond even the population of interstellar visitors. Every object that forms in a protoplanetary disk carries information about the conditions and processes that created it. A frozen archive of the disk's state at the time and location of formation. Solar system comets have provided such information for our own system, revealing that the solar nebula was not uniform, that different regions had different temperatures and compositions, that mixing and transport processes redistributed material in complex ways. Interstellar comets offer the same potential for other systems, but with the profound limitation that we cannot observe the original disk, cannot measure its temperature or density or composition directly, can only infer these properties from the objects it produced. Each interstellar comet is a messenger from a system we cannot visit, carrying news about conditions we cannot observe, speaking in a language that must be decoded through indirect measurements and theoretical modeling. The message is subtle. It is not written in words or diagrams, but encoded in physical properties, the composition of ices and organics, the size distribution and structure of dust grains, the ratio of volatiles to refractories, the isotopic abundances that trace nucleosynthetic origins. Each of these properties connects, through chains of physical reasoning and chemical pathways, to the conditions in the protoplanetary disk where the comet formed. For 3I/Atlas, the polarization signature is one such property, one piece of the message. It tells us something about the dust, about grain sizes or shapes or compositions or porosities. And those grain properties in turn connect to processes in the disk, how grains grew, how they coagulated, what temperatures and pressures they experienced, what organic chemistry occurred on their surfaces or in the surrounding gas. The chain of inference is long, the links sometimes weak, but the connection exists. Other properties provide other pieces. The composition of volatiles, measured through spectroscopy of molecular emissions, reveals what ice is condensed in the disk and at what temperature. The ratio of different isotopes of the same element, if measurable, would reveal the history of the material before it was incorporated into the disk, whether it came from the interstellar medium or was processed through previous generations of stars. The presence or absence of crystalline versus amorphous ice or silicates would indicate whether the material experienced high temperatures that allowed annealing or remained cold throughout its history. Only a comprehensive suite of measurements, covering all these properties and more, could fully decode the message. Only a detailed comparison with models of disk evolution and chemistry could connect the measurements to the original conditions, and only a sample of many interstellar comets, showing how properties correlate or vary across objects from different systems, could reveal the underlying patterns and separate universal features from system-specific variations. The vision is ambitious, perhaps overly so given current capabilities and the rarity of detectable interstellar comets, but it motivates the effort, justifies the investment in observations and modeling, provides a framework for interpreting the data that is collected. Each interstellar comet studied adds to the dataset, narrows the uncertainties, tests the models, brings the vision incrementally closer to reality. 3I/Atlas, with its unexpected polarization signature, demonstrates that the vision is not trivial, that interstellar comets do carry detectable information about their origins, that they do differ from solar system comets in measurable ways, whether the differences are profound or subtle, whether they reveal fundamental variations in disk processes or merely reflect the stochastic scatter of individual formation histories, will become clear only as more objects are studied. The field of interstellar object studies is young, barely a decade old if measured from Oumuamua's discovery in 2017. The sample size is small, the techniques still developing, the theoretical framework still being constructed. But progress is rapid, driven by technological advances in telescopes and detectors, by algorithmic improvements in survey and follow-up strategies, by growing recognition of the scientific value of these objects. Within a decade or two, tens or hundreds of interstellar comets may be known, their properties catalogued, their diversity characterized, patterns will emerge. Some comets will resemble solar system objects closely, suggesting that the processes of planet formation are similar across different stellar systems. Others may show distinct signatures, revealing variations in disk conditions or stellar properties or post-formation processing. Correlations between comet properties and stellar characteristics, metallicity, age, multiplicity may become apparent, connecting the messengers to their origins more directly than is possible with individual objects. 3I/Atlas will be remembered, if at all. As an early example, one of the first interstellar comets studied in detail, one of the objects that established baseline expectations and demonstrated that polarization measurements could reveal differences not apparent in other observables, its polarization signature. Unexpected in 2025 may seem unremarkable once the diversity of the population is better understood, or it may remain unusual, an outlier requiring special explanation, a target for future theoretical work seeking to understand what disk conditions or evolutionary paths could produce such properties. Only time will adjudicate. Only the accumulation of observations and the maturation of theory will place 3I/Atlas in its proper context. For now, the comet serves as a test case, a challenge to existing models, a demonstration that there is still much to learn. The polarization anomaly, neither explained nor dismissed, stands as a reminder that nature is more complex than models capture, that diversity exists even where uniformity might be expected, that every new observation has the potential to surprise. The observers who measured the polarization, who reduced the data and calibrated the uncertainties and published the results, have done their part. They have documented the anomaly, characterized it as well as the data allows, compared it to existing knowledge, and found it wanting in explanation. The theorists who seek to model the observations, who construct scenarios and calculate predictions and test them against the measurements, continue their work, refining models and proposing new observations that could discriminate between hypotheses. The process is slow, iterative, collaborative. No single observation or model provides complete answers. Progress comes through the gradual accumulation of evidence, the narrowing of possibilities, the elimination of hypotheses that fail to match new data, the refinement of those that survive. Science proceeds not by sudden revelation, but by patient investigation, by attention to detail, by willingness to acknowledge uncertainty while still making progress toward understanding. 3I/Atlas, subject of this investigation, continues its journey unaware of the attention, unaffected by the questions it raises. It scatters light according to the properties of its dust, sublimates gas according to the physics of phase transitions and energy balance, moves through space according to gravity and momentum. The processes are deterministic, governed by laws that operate regardless of whether anyone observes or understands them. But the light that scatters from the comet carries information, and humans have built instruments to capture that light, and minds to interpret the information, and communities to share and critique and build upon the interpretations. The comet, indifferent, becomes through this attention more than just a lump of ice and rock. It becomes a data source, a scientific object, a window into processes and places far removed from direct experience. The window is small, the view obscured, the interpretation uncertain, but it is open for now. And those who look through it see not just a comet, but a glimpse of other worlds, other stellar nurseries, other pathways by which matter assembles into the objects that fill the galaxy. The comet passes perihelion in silence, unremarked except by those few who have been tracking its progress, who have invested time and resources in observing this particular speck of light among the millions that populate astronomical images. The moment itself is anticlimactic. There is no visible change, no sudden brightening or alteration in appearance. The comet simply reaches the point of closest approach to the Sun, continues past it, begins the outbound journey that will carry it back to interstellar space, the activity level. Already modest, peaks slightly around perihelion as solar heating reaches its maximum for this trajectory. Water sublimation, suppressed at larger distances, contributes more to the gas production, augmenting the carbon monoxide and carbon dioxide that dominated earlier. The hydrogen coma expands, the ion tail brightens, the dust production increases by a factor measurable in photometry but not dramatic to the eye. The comet remains faint, observable but not spectacular, a target for dedicated observers but not a phenomenon that captures public attention. Only a few thousand people, scattered across the world, know that 3I/Atlas exists. Of those, only a few hundred follow its progress with any regularity. Of those, only a few dozen contribute observations or analysis. The comet's passage through the solar system is, for nearly all of humanity, unnoticed and irrelevant, an event of purely academic interest with no practical implications for daily life or immediate concerns. Yet the academic interest is real, and the implications, if not immediate, extend to fundamental questions about the galaxy and our place in it. How common are planetary systems? How diverse are the processes that form them? Do all stars produce comets, or only some fraction? What happens to the debris left over from planet formation? Does it remain bound to the system, get ejected into interstellar space, accrete onto planets, fall into the star? These questions connect to the origins of life, to the delivery of water and organics to young planets, to the habitability of worlds around other stars. Interstellar comets, as samples from other systems, provide constraints on these questions. Their mere existence confirms that ejection occurs, that planetary systems scatter debris into the galaxy, that material from one system can travel to another. Their properties, composition, structure, activity, reveal what kinds of objects are ejected, whether they differ systematically from those that remain bound, whether interstellar processing alters them in fundamental ways. 3I/Atlas, one object among potentially billions of interstellar comets drifting through the galaxy, cannot answer these questions alone, but it contributes. Its polarization signature, its composition, its activity level, its orbit, all add data points to the emerging picture of the interstellar comet population. The picture is still sketchy, too few data points to reveal clear structure, but each new comet brings it into slightly sharper focus. The final observations of 3I/Atlas are scheduled for the coming weeks. As the comet recedes from the Sun and fades toward the limits of detectability, telescopes will track it as long as possible, measuring its brightness and position, monitoring for any last-minute changes in activity or structure, extracting final spectra and polarization measurements before the signal drops below usable levels. Then, gradually, the observations will cease, not by decision but by necessity. As the comet becomes too faint to detect against the background of stars and sky, the last image will be captured, the last spectrum recorded, the last polarization measurement added to the data set, and then 3I/Atlas will be lost. No longer observable, no longer a target for study. relegated to the status of archived object whose properties are frozen in the data collected during its brief visibility. Future observations are impossible. The comet is leaving, moving away faster than any spacecraft could chase, destined to exit the solar system and return to the interstellar medium from which it came. The trajectory carries it outward through the Kuiper belt, past the scattered disk, beyond the heliopause into true interstellar space. The journey will take years, then decades, the comet gradually cooling as solar heating fades, sublimation ceasing as temperatures drop below the points where even the most volatile ices remain stable, the coma dissipating as the last gas molecules expand away and are lost to space. Eventually, the nucleus will return to the cold equilibrium of interstellar space, 3 Kelvin or thereabouts, warmed only by the faint glow of starlight from the galaxy and the cosmic microwave background. In that state, frozen and inert, the comet will travel for millions of years, perhaps tens of millions, perhaps longer, until the next encounter with a star. The encounter might be distant, a passage tens of thousands of AU away that barely perturbs the trajectory. Or it might be close, bringing the comet into another stellar system's inner regions, triggering another episode of activity, scattering light for observers in that system, if any exist, offering them the same opportunity that 3E/Atlas offered to humanity. A chance to study a visitor from elsewhere, to learn from its properties, to wonder about its origins. But those observers, if they exist, will not know about 3I/Atlas's passage through our solar system. They will not have access to the data collected here, will not benefit from the measurements made by terrestrial telescopes. Each encounter is isolated, each observation independent. The comet connects systems physically, traveling between them, but it does not transmit information. It carries no message, no record of its previous visits, no data about the systems it has passed through. It is simply matter, ice and rock and dust, moving through space, occasionally illuminated, most often dark and invisible. The human record of 3I/Atlas will persist as long as human civilization preserves it, as long as archives are maintained and data remains accessible. The observations, published in journals and stored in databases, will be available to future researchers, will serve as historical reference points, will document what was known in this era about this particular comet. But the comet itself, the physical object, will be gone, irretrievable, moving along a trajectory that diverges ever further from the solar system, becoming less and less likely to ever return. This finality is inherent to interstellar comets. They visit once, briefly, and depart forever. There are no second chances, no opportunities for follow-up missions or improved observations with next-generation instruments. What is captured during the passage is all there will ever be. The pressure to observe, to collect as much data as possible while the opportunity exists, drives the intensity of the effort. The long nights at telescopes, the careful calibration and reduction of data, the rapid publication to share results with the community while the comet is still observable and follow-up measurements might still be possible. For 3I/Atlas, that window is closing. The comet fades day by day, magnitude by magnitude, the signal-to-noise ratio declining as the inverse square law asserts its dominance. Soon, only the largest telescopes will be able to detect it. Then, only under perfect conditions. Then, not at all. The moment of visibility, which seemed generous when the comet was first discovered months ago, now feels brief, insufficient, leaving questions unanswered and measurements uncompleted. The polarization anomaly will remain unexplained, at least for now. The models will continue to evolve. The hypotheses will be refined, but without additional data from this comet, definitive conclusions remain out of reach. The ambiguity persists, encoded in the published uncertainties, acknowledged in the discussion sections of papers, accepted as the inevitable consequence of studying objects that cannot be controlled, cannot be revisited, can only be observed as they are. From where they are, with whatever instruments happen to be available, future interstellar comets will benefit from the experience gained with 3Y/Atlas. Observation strategies will be optimized, having learned which measurements are most valuable and which constraints are most critical. Theoretical models will be better developed, ready to interpret new data more efficiently. The community will be prepared, organized, able to mobilize resources quickly when the next visitor is detected, and the next visitor will come. The detection rate suggests that interstellar comets pass through the inner solar system regularly, perhaps several per year, though most are too faint or too poorly positioned to be discovered with current survey capabilities. As those capabilities improve, as new telescopes come online with larger apertures and wider fields and more sensitive detectors, the detection rate will increase. Within years, perhaps a decade, interstellar comets might become routine targets, studied systematically rather than opportunistically, contributing steady streams of data rather than occasional snapshots. 3I/Atlas then represents a transitional moment in the field, early enough that each detection is still novel, still worthy of intensive study, still treated as a special event, late enough that the techniques are developed, the community is established, the scientific questions are articulated clearly. Future historians of astronomy might look back on this period as the beginning of interstellar comet science as a mature discipline, when the field moved from discovery and characterization to systematic investigation and comparative analysis. The comet itself cares nothing for such narratives. It continues outward, sublimating weakly, scattering diminishing amounts of light, following the trajectory determined by its velocity and the sun's gravity. The dust grains it ejects now will be among the last. As activity declines toward zero and the nucleus returns to dormancy, those final grains will drift into the tail, will disperse into interplanetary space, will become part of the solar system's zodiacal dust cloud, or be ejected by radiation pressure, or swept up by planets. Their origin in an interstellar comet will be impossible to determine from their properties alone. They will simply be dust, indistinguishable from the countless other particles that fill the space between planets. Only the archival data will preserve the memory that these grains came from 3I/Atlas, that they originated in another stellar system, that they traveled millions of years through interstellar space before briefly illuminating in our sun's light and scattering into obscurity. The data connects observation to history, photons to origins, measurements to meaning. Without the data, the grains are anonymous. With it, they are traceable, their provenance at least partially known, their properties contextualized within the larger story of the comet and its journey. The story has no proper ending, no resolution, no climax or denouement. The comet arrived, was observed, provided data, and will depart. The polarization signature was measured and found to be unexpected. Explanations were proposed but remain unconfirmed. Questions were raised that may not be answered for years or decades. The narrative, such as it is, simply trails off, unfinished. The protagonist receding into darkness, leaving behind only traces and speculation. This is typical of astronomical research. Most objects do not provide neat conclusions. Most observations raise as many questions as they answer. Progress comes not from individual studies reaching completion, but from the accumulation of many incomplete studies, each adding fragments of understanding that eventually coalesce into broader knowledge. 3I/Atlas is one fragment, one piece of a puzzle too large to see clearly, contributing its small part to a picture that spans the galaxy and encompasses billions of years of cosmic history. The observers pack up their equipment, submit their final data products to archives, begin writing papers summarizing the results. The comet recedes beyond detection, beyond observation, beyond influence. The telescopes turn to other targets, other projects, other questions. The specialized community that formed around 3I/Atlas disperses, its members returning to their regular research programs, though some will continue analyzing the data, mining it for additional insights, comparing it with future observations of other comets. The dust grains scattered by the comet continue their individual journeys, each on a slightly different trajectory, each experiencing slightly different forces from radiation pressure and solar wind and planetary gravitational fields. Over years and centuries, they will spread, filling a volume of space that grows steadily larger, the density dropping as the distribution expands. Eventually, they will be so dispersed that the probability of any single grain being identified or even encountered becomes negligible. The comet itself crosses beyond Neptune's orbit, entering the region where solar influence begins to fade and interstellar conditions begin to reassert themselves. The temperature drops toward the asymptotic 3 Kelvin, the cosmic ray flux increases as the heliosphere's shielding weakens. The comet returns to the environment it has known for most of its existence. The cold darkness between stars, the patient drift through the galaxy. Ahead lies the heliopause, the boundary where solar wind pressure balances interstellar pressure, where the sun's domain truly ends and the interstellar medium begins. The comet will cross this boundary in a few years, will leave the solar system not just in the gravitational sense, which it never entered, its orbit always unbound, but in the environmental sense, exiting the bubble of solar influence and re-entering the galactic background. Beyond that boundary, the comet will be alone again, as it was before, moving at constant velocity through space that is empty on human scales, but filled with atoms and photons and magnetic fields on cosmic scales. The journey will continue, timeless and unchanging, until the next encounter with a star, whenever and wherever that might be. The universe is patient, the galaxy is vast, the comet has time, endless time, drifting through the slow currents of galactic motion, rising and falling through the disk, passing through spiral arms, approaching and receding from molecular clouds, indifferent to everything except the mathematics of gravity and the thermodynamics of radiation and matter. And somewhere, receding behind it, a small rocky planet orbits a yellow star, and on that planet, a few thousand individuals remember, for a little while, that something called 3I/Atlas passed through their corner of the cosmos, scattered some light, posed some questions, and moved on. The light fades, not suddenly but gradually, dimming with each million kilometers of increasing distance, each passing day adding to the separation between the comet and the instruments that observe it. The signal weakens, the noise grows relatively stronger, the measurements become less certain, the error bars expand. There comes a moment, impossible to define precisely, when the comet transitions from observable to unobservable, when the last useful photon is captured and all subsequent light is lost in the background, indistinguishable from noise. After that moment, the comet exists only in memory and data. The physical object continues, of course, moving through space according to laws that require no observation to operate, but for human purposes, for scientific purposes, it has departed, joined the vast population of objects too distant or too faint to study, relegated to the category of things known to exist but no longer accessible. The data remains, numbers in tables, images in archives, spectra stored in standard formats, polarization measurements preserved with their calibration files and reduction notes. These digital remnants outlast the observations, persist beyond the moment of visibility, carry forward the information extracted during the brief window when the comet was close enough and bright enough to study, the polarization signature, unexpected and unexplained, sits in those archives, waiting for new models, for new comparison objects, for new theoretical insights that might finally decode what the twisted photons were trying to say about the grains that scattered them. The wait might be long, years, decades, perhaps longer, or perhaps the next interstellar comet, or the one after that, will show a similar signature, and the pattern will emerge, and understanding will follow, but that is future. For now, there is only the fading, the gradual recession, the slow diminishment of signal until it merges with silence. The comet does not notice its own disappearance from human awareness. It continues outward, crossing invisible boundaries, passing milestones that exist only in human conceptual frameworks. The orbit of Pluto, the scattered disk, the heliopause ahead. Each crossing is just another moment in an endless sequence of moments, no more significant than any other, marked only by human observers who assign meaning to positions in space. The nucleus cools. Sublimation slows, then stops. The coma thins, becomes transparent, fades into non-existence. The tails dissipate, the particles dispersing, the ions recombining or being swept away by the solar wind, the dust spreading along diverging trajectories. What remains is just the nucleus, dark and silent, returning to the dormancy it maintained for millions of years before this brief interlude of activity. In that dormant state, frozen and inert, the comet will travel onward, past the heliopause, into interstellar space proper, through the local bubble and beyond, moving with the general rotation of the galaxy, but also with its own peculiar velocity, its own trajectory through the three-dimensional space of the Milky Way's disk. Where it goes, no one can say with certainty. The trajectory is calculable for years, perhaps decades, but beyond that, perturbations accumulate, uncertainties grow, and prediction becomes speculation. A close pass by a star centuries from now could alter the path significantly. Passage through a molecular cloud could slow it slightly through drag. The galaxy's gravitational field, complex and time-varying on million-year scales, will curve the trajectory in ways that depend on mass distributions that are themselves uncertain. The comet will go where it goes, indifferent to predictions, following only the immediate forces acting on it, responsive only to gravity and the vanishingly small pressures of radiation and gas in the interstellar medium. Time passes. The comet recedes. The data sits in archives, accessed occasionally by researchers, mostly dormant, waiting for context that might give it new meaning. The universe continues its slow evolution. Stars form and die. Molecular clouds collapse and disperse. The galaxy rotates, its spiral arms migrating, its disk rising and falling in response to gravitational waves and tidal interactions with satellite galaxies. And through all this, the comet drifts, a tiny speck of frozen matter, carrying in its ice and dust a record of processes that occurred billions of years ago in a place no human will ever see, around a star no human will ever visit, preserving information that might never be fully decoded but exists nonetheless, encoded in grain sizes and ice ratios and isotopic abundances, waiting. The waiting is patient. The waiting is eternal. The waiting requires nothing and expects nothing and simply is, a state of being that continues whether or not anyone remembers or cares or understands. The comet sleeps. If sleep is the right word for the dormancy of frozen matter in the cold dark between stars, it does not dream, it does not remember, it simply is, and continues to be, drifting through the vastness. One small object among uncountable trillions, unremarkable except for the brief moment when light touched it and scattered and carried information across the void to curious minds that wondered what it meant. The moment passed, the light faded, The wondering continues, for a while, then it too will fade, will be forgotten, will join the countless other questions that were asked and left unanswered, lost to time and the frailty of memory and the vastness of all there is to know, somewhere in the galaxy. The comet continues its journey. Somewhere in archives, the data persists. Somewhere between these facts lies meaning, if meaning is the right word, or simply information, or simply the trace of an encounter between matter and mind, between photons and curiosity. Between the universe as it is and the universe as we try to understand it, the polarization signature was unexpected. The comet does not know this. It scattered light according to its properties, nothing more, nothing less. The expectation was human. The surprise was human. The wonder, the curiosity, the effort to understand, all human. The comet participated only by existing, by being what it was, by passing through at the right time and distance to be observable. And now it passes on, leaving behind data and questions and the faint hope that someday, somehow, the pattern will become clear and the unexpected will transform into the understood. But for now, in this moment that stretches into stillness, there is only the fading light, the cooling ice, the patient dark, and the slow, certain drift of one small comet through the immensity of space and time